Hi friends, welcome to our YouTube channel Knowledge Academy. The main aim of this lecture is to discuss about the choppers in a very detailed manner. And if you like the content of our channel, then please to like, share and subscribe our YouTube channel and don't forget to press the bell icon button. So whenever we upload new video, the direct notification comes to your mobile. If any information needed in our lectures, then please look in the comment section. We will definitely include all those information in the coming lectures. So why to waste more time? So let's get started. First concept that we are going to deal is the step down chopper. See, step down chopper means always the output voltage will be always lesser than the input voltage. The basic agenda of chopper is to the basic function of chopper is to convert a DC voltage into a variable DC voltage. The basic function of chopper is to convert a fixed DC voltage into a variable DC voltage. That is the basic function of a chopper. So now we are going to discuss about the step down chopper means always the output voltage will be always lesser than the input voltage. So now we are going to see this one with the help of an R load. So we are going to keep here R load. So this is a fixed DC voltage which is plus or minus Vs. So here we are going to connect an R load. So R load is going to consume a current of I0 with a load voltage of plus or minus V0. So this is basically a chopper means it is basically a switch. So this is a switching operation. So basically it is a chopper means it is basically doing a switching operation. So this is a chopper. So the voltage across the chopper or the switch is VCH. So now we are going to see this one. The graphs we are going to now do the analysis of this one. See, as the input voltage is a fixed DC voltage of Vs for all the time is a fixed DC voltage Vs. So now I am going to do this gating means I am going to turn on the chopper for some amount of time and then I am going to turn off. So for 0 to T and T on I am going to turn on the chopper, and after that from T on to T I am going to turn off. So this I am going to do it on a repetitive basis at a time period of T. So I am going to repeat this process after every time period T. So therefore here whenever the chopper is on, it means the switch is on. So therefore the output voltage is equal to Vs. So output voltage is equal to Vs. So therefore the output current is equal to output voltage by R, which is Vs by R. As the chopper is on, so voltage drop across it is ideally it is equal to 0. Whenever the chopper is off, means switch is open, so therefore the V0 is equal to 0 because it is open circuit, and current is also equal to 0 because the output voltage itself is equal to 0. See, whenever the chopper is open, whatever supply voltage is totally dropped across the chopper. So therefore the voltage across the chopper is equal to supply voltage Vs. So this process is going to get repeat after the time period of T. So same process is going to get repeat. So whenever the chopper is on, the output voltage is equal to Vs, output current is equal to Vs by R, and the chopper voltage is equal to 0. Whenever the chopper is off, so output voltage is equal to 0, output current is equal to 0, and the chopper voltage is equal to supply voltage. So this is how these graphs are going to repeat after time period T. So now we are going to do some analysis of this circuit. Some analysis of the circuit we are going to see. See, I want to find what is the average voltage of the output voltage. So basically I want to find what is the average value of the output voltage. So V0 average is equal to Vs into T on by T. So Vs into T on by T. So T on by T is called the duty ratio. So turn on by total time period. The ratio of T on by total time period is called the duty ratio, which is D into Vs. So therefore this is called as a D into Vs. So the average value of the output voltage is equal to D into Vs. So you can see clearly D value is going to lie from 0 to 1. So D value is going to lie from 0 to 1. So when D is 0, V0 average is equal to 0. When D is equal to 1, V0 average is equal to Vs. So therefore the average value of the output voltage is going to lie from 0 to Vs because D is going to vary from 0 to 1. So now I want to find what is the average value of the output current. So average value of the output current is equal to average value of the output voltage by R. So therefore you are going to get D into Vs by R. So this is the thing which you are going to get. So similarly I want to find what is the RMS value of the output voltage is equal to Vs into under root over T1 by T. T1 by T is called the duty ratio. Therefore Vs into under root over D. Similarly, the RMS value of the output current is equal to RMS value of the output voltage by R. So this value just now we have did, it is root 2 into Vs by R. Similarly, form factor is equal to, form factor means easy to remember is FRA. Form factor is the ratio of the RMS value by the average value. The RMS value of the output voltage by the average value of the output voltage. So you know both the things, just do the division of these two things, and finally you are going to get 1 by root D. So 1 by root D, 1 by root D you are going to get. This is called as the form factor. So if you want the ripple factor, which is under root over form factor whole square minus 1. So if you substitute here, we are going to get under root over 1 minus D by D. So these are the things that you are going to get finally with the help of this graph. So now we are going to connect the RL load. So now we are going to connect the RL load. So this is the RL load we are going to connect with a freewheeling diode. So this is the RL load with a freewheeling diode. So now we are going to basically analyze this circuit. The supply voltage is plus or minus Vs and the output voltage is plus or minus V0. And this is the output current is I0. This is basically a chopper, or basically it is also called as a switch. So this is freewheeling diode and the current in the freewheeling diode is IFD. So now we are going to basically analyze this circuit. As I have already told you, the supply voltage is constant for all the time. So this is Vs. So Vs is the supply voltage, it is constant for all the time. So therefore, and I have already told you, we are going to switching this process, we are going to switch on for some amount of time, that is called as a T-on. So T-on is the time for which we are going to turn on the switch or the chopper. After that, we are going to give some time period from T-on to T, it is called as T-off. During this period, I am going to turn off the thyristor, the chopper, so which is open. So this process I am going to repeat on the daily, on the same after a period of time, I am going to repeat this process. So then I want to see what is the nature of the output voltage, output current, each and everything I want to see and analyze this one. So whenever the chopper is on, so you can see clearly the supply voltage is equal to, the output voltage is equal to supply voltage. So we are going to get in this manner. But whenever the chopper is off, it is open, so you can say that the output voltage is equal to 0. So output voltage is equal to 0. So whenever the chopper is on, the output voltage is equal to supply voltage and the inductor is going to get charged. So now you can see clearly here, whenever the chopper is on, so output voltage is equal to supply voltage and inductor is going to get charged. So therefore current is going to become a charging, means it will be rising. So therefore we can say it will be rising from minimum value to maximum value. And see, whenever we are going to assume that the inductance of this inductor is very low, then only it is going to behave like this. So whenever from T on to T, chopper is off, so therefore the inductor is going to discharge its energy through this freewheeling diode. So therefore it is going to, the current is going to discharge, means basically the inductor is going to discharge its energy. So therefore current is going to decay. So this is what it is going to decay from maximum value to minimum value, and this it is going to repeat that further and further. So when the inductance is low, I want to even draw the freewheeling diode current. See, freewheeling diode is going to conduct only from T on to T. So whatever the current in the output, so whatever the current I0 will be same as the IFD only from T on to T, and in the remaining time period it is off, so the reference current is equal to 0. From T on to T it is going to conduct, so whatever the output current is going to same, it is going to flow to the same to the freewheeling diode. So this is the nature of the freewheeling diode current we are going to get whenever the inductance is low. Suppose if the inductance is very high, what is going to happen? If the inductance is very high, then the output current will be almost constant. It will be almost constant because like I0, it's a constant current for all the time, because the inductance what we have taken is very high value. So because of that, the output current is almost constant with respect to time. So because of that, I want to draw even the freewheeling diode. I have already told you, freewheeling diode is only connecting from only T on to T. So in the remaining time it is off, so its current is equal to 0. But from T on to T it is connecting, so whatever the output current in this time period, it is same as the freewheeling diode current. So therefore this is the nature we are going to get. So this is the output current and the freewheeling diode current whenever the source, whenever the load inductance is very high, and the remaining about two graphs are when the load inductance is low. So you can see from 0 to T on, chopper is on, so freewheeling diode is off. Similarly, from T on to T, freewheeling diode is on, so chopper is off. The red symbol indicates that these are on, and this blue symbol indicates that they are off. So these are the graphs that we are going to get when the load inductance is low and the load inductance is high. So now I want to find what is the analysis of this circuit. So for this RL load, I want to do the analysis. As you can see clearly, the average value of the output voltage is equal to Vs into T1 by T, which is equal to Vs into D. So therefore, this is called as the D into Vs. So simply we call it as the. So step down chopper means the average value of the output voltage is equal to D into Vs. I have already told you D is going to lie from 0 to 1. So therefore, V and average is also going to lie from 0 to Vs. And I have already told you the RMS value of the output voltage is equal to, simply if you want the RMS value, which is Vs into under root over T1 by T, which is called as a Vs into under root over D. Similarly, the average value of the output current is equal to, so the average value of the output current is equal to the average value of the output voltage by R. So see, basically what will be like this. See, average value of the output voltage by R, it is called as the, see basically what is going to happen, very simple. So V naught average is equal to I naught average into R plus VL average, but VL average is equal to 0. So because of that, V naught average is equal to I naught average into R. So therefore, I naught average is equal to V naught average by R. Similarly, I want to find what is the freewheeling diode average current. So the average value of the freewheeling diode current, whenever see this is the, whenever I assume that the load inductance is very high, the average value I want to figure out. So basically very simple. So I naught average into, so I naught average into, this is I naught average into T minus T on by capital T. So T minus T on by capital T, it is nothing but simply we are going to get 1 minus D into I naught average. So this is called as a freewheeling diode average current. So average value of the freewheeling diode current is equal to I naught average into T minus capital T minus T on by capital T. So if you do this one, we are going to get finally 1 minus D into I naught average. This is the average value of the freewheeling diode current. So now we are going to discuss the step up chopper. So now basically now we are going to study about the step up chopper. So in the step up chopper, the circuit diagram of the step up chopper is like this. So this is the inductor, and this is the chopper, and this is the diode, and this is the load resistor. It's like S, this is switch S, V, L. This is the way that you need to remember. So whereas for the step down chopper, it will be S, V, L. So S, V, L for the step down chopper, and here S, V, L like this. Just I give a clockwise, anti-clockwise shift like this. So for the step down chopper, S, V, L. But here for the step up chopper, just give a phase shift of in the anti-clockwise direction. So just give a clockwise there, or you can say in the anti-clockwise direction, just give a shift. So S, V, L. So this is the circuit diagram we are going to get. Switch, chopper, diode and inductor. The supply voltage is plus or minus Vs, and the output resistor is R, the load resistor is R, and the output voltage is plus or minus V naught, and the output current is I naught. So I have already told you the supply voltage is always constant for all the time. And I have already told you here I am going to do the switching operation of this chopper. For a 0 to T on, I am going to turn on the chopper. From T on to T, it is called as a T off, means I am going to open the switch. See, whenever the chopper is on, so whenever the chopper is on, you can see clearly that the output voltage is equal to 0. So whenever the chopper is on, you can see from the circuit diagram that the output voltage is equal to 0, means the inductor is going to become charging. So the inductor current, so IL is the inductor current. So the inductor current is going to get charged. So IL is the current in the inductor, it is basically going to get charged from I minimum to I maximum. So we can say clearly in that period the diode is off. So therefore, or simply we can say that the output voltage is equal to 0. So therefore the output current is also equal to 0 in that range. Similarly for T on to T, we have opened the chopper. So as the chopper is open, we can say clearly that the output voltage is the summation of the supply voltage and also the inductor voltage. So from T on to T, we can say that the output voltage is a summation of the source voltage and also the inductor voltage, which is VL plus Vs. So now the inductor is going to discharge its energy into the resistor, so the current is going to get decay. Similarly, now the diode is going to get conduct, so therefore the output current is same as the inductor current, so therefore the output current is the same as the inductor current in this range. So same graph is going to get repeated. So whenever the chopper is on, so the output voltage is equal to 0, the output current is equal to 0, so the inductor current is going to get charged from I minimum to I maximum. When the chopper is off, the output voltage is the summation of the load voltage and the inductor voltage and also the source voltage. So therefore now here as the inductor is going to discharge its energy, so current is going to get decay. So therefore now the output current is the same as the inductor current, so it is going to follow the inductor current. So same thing is going to get repeated. So you can see clearly the inductor current is a triangular in shape. Whereas the output current is a trapezoidal in shape. So the inductor current is a triangle in shape, whereas the output current is a trapezoidal in shape. So we are going to analyze this circuit in a very detailed manner. The first case is I am going to turn on the chopper. So when the chopper is turned on, this is the circuit diagram I am going to get. So this is plus or minus Vs. So this is an inductor. So inductor means the chopper is on. So therefore whenever the chopper is on, the diode is going to act like a reverse bias. So this open circuit, the output current is equal to 0. So therefore the output voltage is also equal to 0. See, for the inductor we have given a supply voltage DC. So it is going to get charged. So inductor is going to get charged. So therefore if you apply the KVL, which is plus or minus load voltage VL, the inductor voltage is VL and the inductor current is IL. So if you apply the KVL in this node, we are going to get VL is equal to Vs. So therefore we can say that as the chopper is on, the output voltage is equal to 0, output current is equal to 0, inductor is charging, so therefore IL is going to go from I minimum to I maximum, and also the output current is equal to 0. So when the chopper is off, in the previous case the inductor is going to store the energy, means plus or minus VL and this IL. Now the chopper is off, so whenever the chopper is off, which it is open, means whatever the energy stored in the inductor should be released. So now the inductor is going to deliver the energy. So current in the inductor cannot change its direction instantaneously. So therefore the voltage across the inductor is going to get reversed to deliver the energy. So therefore now this inductor is going to deliver the energy. This is plus or minus VL. So if you apply the KVL in this node, we are going to get V0 is equal to Vs plus VL. V0 is equal to Vs plus VL. So if you apply the KCL here, IL is equal to I0. So IL is equal to I0. The inductor is going to get discharged. So whenever the chopper is off, the output voltage is the summation of the source voltage and the inductor voltage, and the inductor is going to get discharged. So therefore the IL is equal to I0. So now I am going to apply a basic principle which is very much applicable for each and every circuit in the chopper. Whatever the energy stored in the inductor in the charging mode is equal to the energy delivered by the inductor in the discharging mode. So listen carefully. Whatever the energy stored in the inductor during the charging mode is equal to energy delivered by the inductor in the discharging mode for the inductor. In the charging mode, I want to apply what is the energy. So VL IL into T on is equal to VL IL into T off. So this is the energy stored in the inductor during the charging period, and this is the energy delivered by the inductor during the turn off period, during the discharging period. So VL IL into T on is equal to VL IL into T off. So during the turn, whenever the chopper is on, the inductor voltage is equal to supply voltage. So inductor current is IL. So this is T on is equal to, now when the chopper is off, so therefore if you apply the KVL, then VL is equal to V0 minus Vs. So VL is equal to V0 minus Vs. So VL is equal to V0 minus Vs into, so this is IL into T off. So because it is discharging energy, so therefore VL is equal to V0 minus Vs into IL into T off. So if you analyze, if you solve this equation, finally we are going to get V0 is equal to Vs by 1 minus D. So therefore the average value of the output voltage is equal to supply voltage by 1 minus D. So this is the equation we are going to get between the input and the output. So we have to remember only one concept. Whatever the energy stored in the inductor during the turn on period is equal to energy discharged by the inductor during the turn off. So VL IL T on is equal to VL IL T off. So in the charging, when the chopper is on, VL is equal to VS IL into T on is equal to, when the chopper is off, the voltage polarity is going to get reversed. So therefore VL is equal to V0 minus Vs into IL into T off. So if you solve this equation, we are going to get V0 is equal to Vs by 1 minus E, where D is a duty ratio which is equal to ratio of T1 by T. So D can lie from 0 to 1. So if D is equal to 0, then V0 is equal to Vs. If D is equal to 0, then V0 is equal to Vs. If D is equal to 1, V0 is equal to infinity. So therefore V0 is going to lie from Vs to infinity. So V0 is going to lie from Vs to infinity. So therefore we can say that simply the average value of the output voltage is going to lie from Vs to infinity. So you can say clearly always the output voltage is greater than the input voltage. So this is called as a step up chopper. So average value of the output voltage is always greater than the or equal to the input voltage. So because of this reason only we call it as the step up chopper. So now we are going to discuss about the step down and the step up chopper, or you can say step down and up converter. It's a combination of both the step down and also the step up converter. So this is basically the circuit diagram of the step down and step up converter. So this is the switch on the chopper. So here inductor and is the diode. So this is the circuit diagram of this step up and step down converter. So basically this is the supply voltage plus or minus Vs, and the output voltage. See, output voltage polarity is now reversed. It is plus or minus V0, and the output current is from I0. So this is the downward direction we need to always remember. So this is the inductor L, and the current in the inductor is IL. So with the help of this, now we are going to analyze the circuit when the chopper is on and also when the chopper is off. So when the chopper is on, see, when the chopper is on, so you are going to close the chopper, and this is the inductor. So you can see clearly whatever the supply voltage is equal to voltage across the inductor. So inductor is going to become charged. As the inductor is charged, so this will become open circuit, means no current is going to flow to the diode. So therefore the I0 is equal to 0 and also V0 is equal to 0. So when the chopper is on, whatever the load voltage, whatever the inductor voltage is equal to voltage of the supply voltage. So L is charging. So therefore the current IL is going to charge. Therefore the output voltage is equal to 0 and also the output current is equal to 0. So what happens if the chopper is off? If the chopper is open circuit, whatever the energy stored in the inductor is going to deliver to the resistor. So here in the previous case, the inductor is going to absorb the energy, but now the inductor is going to deliver the energy. So current in the inductor cannot change its direction, so therefore the polarity of the voltage should be changed. Then only it is going to deliver the energy. So therefore, whenever the chopper is off, whatever the output voltage is equal to voltage across the inductor, and the inductor is going to discharge. So you can see clearly the inductor current is equal to output current, or simply the output current is equal to inductor current. So now we are going to apply the energy stored in the inductor during the charging mode, and also whatever the energy discharged by the inductor during the discharging mode, both should be equal for the inductor. So when the chopper is on, the inductor is charging, so therefore VL IL T on is equal to, during the discharging mode when the chopper is off, the energy discharged by the inductor is VL IL T off. So here in both the cases IL is same, so IL we are going to get cancelled. Whereas VL, so VL is nothing but in the charging mode VL is equal to Vs, whereas in the discharging mode VL is equal to V0. So Vs into T on is equal to V0 into T off. So if you solve this one, we are going to get finally V0 is equal to Vs into D by 1 minus D. So you can see clearly this is a combination of both the step down and also the step up, because the step down voltage V0 is equal to D into Vs, whereas the step up voltage is V0 is equal to Vs into Vs by 1 minus D. So you can see clearly this is a combination of both the step down and also the step up. So V0 is equal to Vs into D by 1 minus D. So D value is going to lie from 0 to 1. This I think I have already told you. So if D is equal to 0, if you substitute D is equal to 0, we are going to get V0 is equal to 0. If D is equal to half, then we are going to get V0 is equal to Vs. If D is equal to 1, then V naught is equal to infinity. So you can see clearly when these lying from 0 to half, the average value of the output voltage is lying from 0 to Vs. So we can say this is called as a step down chopper because the output voltage is less than the input voltage. Whereas these lying from half to 1, the average value of the output voltage is greater than supply voltage. So it is going to act like a step up chopper. So whenever the D is lying from 0 to half, it is going to act like a step down chopper. And whenever the D is lying from half to 1, it is going to act like a step up chopper. So this is the basic agenda of this step up and step down converter. So the circuit diagram is going to do the function of both the choppers, step down and also step up, by varying the value of the D. Let us learn some important basic concepts in the chopper. The basic concepts in the chopper are, which is D is called as a duty ratio. It is a ratio of the T1 by T. So duty ratio is the ratio of the T1 by T. Where T is called as the total time period, it is a summation of T1 plus T off. So T is called as the summation of T1 plus T off. So T off is equal to, T off is equal to T minus T on. So T off is equal to T minus T on. So whereas T on is equal to D into T, substitute here we are going to get T into 1 minus T. Similarly, T on is equal to T into D. You can write either in these two formats. So always the average value of the inductor voltage will be always equal to 0. Similarly, the average value of the capacitor current will be always equal to 0. So this is the important point that you always have to remember, which is the average value of the inductor voltage will be always equal to 0. Similarly, the average value of the capacitor current will be always equal to 0. So therefore, VL on into T on plus VL off into T off is equal to 0. IC on into T on plus IC off into T off is equal to 0. So always the average value of the inductor voltage will be always equal to 0. Similarly, the average value of the capacitor current is also equal to 0. So now we are going to study about the buck converter or the step down chopper. So this is basically continuous conduction mode. See, buck converter is also called as the step down chopper. Buck converter is also called as the step down chopper. Means the average value of the output voltage is always lesser than the source voltage. So this is always a continuous conduction mode. So this is the circuit diagram of this buck converter. So this is the supply voltage. So the easy way to remember is, here there is a chopper SDL. SDL. The diode is like upper. So therefore SDL. So this is the load. For load always we are going to connect a capacitor. So because I don't want a large amount of variation in the output voltage. So because of that reason only I am going to connect a capacitor across the load. So therefore the capacitor, the voltage across the capacitor cannot change instantaneously. So because of that reason only there will be no large variation in the capacitor and the output voltage. So always I am going to assume the value, whatever the value of the inductor I am going to choose is always greater than the LCR, which is critical inductance. Always whatever the inductance I am going to choose here in the circuit is always greater than the critical inductance. Then only continuous conduction mode is possible. So this is the basically circuit diagram. So this is the source current IS and this is the switch current ISW, and this is the inductor current IL, and the inductor voltage is plus or minus VL, and this is the output current I0, and this is the output voltage V0, and this is the capacitor voltage plus or minus VC, and this is the capacitor current IC. So these are the each and every aspect of this graph. So SDL. So this is the thing that you need to remember. So based on this, now we are going to analyze each and every aspect of this circuit diagram. See, when I turn on the switch, what is going to happen? When I turn on the switch, here you can see clearly that the inductor is going to get charged. So therefore, the inductor is going to get charged means the inductor current is going to go from minimum value to a maximum value. So the minimum value is IL minimum to IL maximum whenever the switch is on. So now the capacitor current, so this load current is going to divide into two components, the capacitor current and also the load current I0. So then if I want IC, which is IL minus I0, so if you remove I0 from IL, you are going to get the only ripple you are going to get. So this is the ripple that you are going to get, which is IC. So the capacitor voltage will be in this format. the capacitor voltage from maximum value to minimum value, there will be a small amount of variation. When the switch is off means, basically we can say it is open. So therefore, whatever the energy stored in the inductor, now it is going to deliver to the load. So therefore, we can say the current in the inductor is going to become now discharging. It is going to decay. So same thing again, IC is nothing but IL minus I naught. So if you remove I naught from this IL, you are going to get only the ripple you are going to get. And the capacitor voltage will be in this format. So same thing is going to again repeat. So therefore here the IL, so therefore the amount of variation from IL minimum to IL maximum, this amount of ripple is called as delta IL. So delta IL is the amount of ripple in the inductor current IL. So delta IL is called as a ripple in the IL. So therefore, if I take the average value of this inductor current, the average value of the inductor current in this format, it is going to lie between the IL minimum and the IL maximum. So IL average is going to lie in between the IL minimum and the IL maximum. So this is called as delta IL by 2 and this is the delta IL by 2. So therefore it is going to be, it is basically a midpoint. It is a midpoint of this IL minimum and IL maximum. So this is delta IL by 2 and this is delta IL by 2. So we can say clearly IL average is equal to IL minimum plus delta IL by 2, or IL average is equal to IL maximum minus delta IL by 2. So delta IL is called as a ripple. So the average value here, the average value of the inductor, the average value of the inductor current is equal to I naught. So because I have already told you IL is equal to I naught plus IC. So IL average is equal to I naught average plus IC average, as IC average is equal to 0, because the average value of the capacitor current is always equal to 0. So therefore IL average is equal to I naught. This is the thing that you always have to remember in this circuit. So IL average is equal to I naught. Similarly, if IC is equal to IL minus I naught, so you are going to get in this format. So I have already told you this overall is the delta L, the ripple is delta L. So this is delta L by 2 and this is minus delta L by 2. So therefore this is plus delta L by 2 and this is minus delta L by 2. So therefore I have already told you the average value of the capacitor current is always equal to 0. Similarly, the average value of the capacitor voltage is equal to load voltage, which is V0. So but the actual graph is going to look in this format. So the amount of ripple in the output voltage or the capacitor voltage is delta Vc. So delta Vc is the amount of ripple in the output voltage or the capacitor voltage. So the average value of the capacitor voltage is equal to the output voltage itself. So now we are going to basically analyze this each and every aspect. So now we are going to analyze this one. So what is going to happen? See, whenever the switch is on, what is going to happen? Whenever the switch is on, you can see clearly that VL is equal to the voltage across the inductor during the on time is equal to Vs minus V0. So therefore VL on means the inductor voltage during the chopper is on is or the switch is on is equal to Vs minus V0. We can get from the circuit. Similarly, IC on is equal to, so IC on is equal to IL minus I naught. So therefore IC on is equal to IL minus I naught. So whenever the switch is on, the capacitor current IC on is equal to IL minus I naught. You can get from the circuit itself. Whenever the switch is off, so whenever the switch is off, whatever the, see, VL off is equal to, because VL off and V0 are in opposite polarity, so therefore VL off is equal to minus V0. You can get from the circuit diagram. So therefore IC off is equal to, same thing, again we are going to get IL minus I naught. So IC off is equal to IL minus I naught. I am going to assume that load is very highly inductive, so therefore output current is almost constant. I am going to assume that load is highly inductive, so therefore the output current is almost constant. So I am going to assume that I naught current is always constant. I am also going to assume that L and C are greater than the critical inductance. So L and C are the values which are more than the critical inductance and the critical capacitance. So therefore the continuous conduction is possible. So I have already told you the average value of the inductor voltage is always equal to 0 and the average value of the capacitor current is always equal to 0. So therefore VL on into T on plus VL off into T off is equal to 0. So VL on is nothing but Vs minus V0. T on is equal to D into T and VL off is nothing but minus V0 into T off is nothing but 1 minus D into T is equal to 0. So if we solve this equation, we are going to get V0 is equal to D into Vs. So the average value of the output voltage is equal to D into Vs. So the average value of the output voltage is equal to D into Vs. I already told you D is going to lie from 0 to 1. See, continuous conduction means the current in the inductor is not at all 0. It is not at all 0. That is the reason it is a continuous conduction mode. You can see clearly the current in the inductor is not at all 0. For not even one time it is 0. So because of that only we can say it is a continuous conduction mode is present. And I have already told you the average value of the capacitor current is always equal to 0, which is IC on into T on plus IC off into T off is equal to 0, as IC on is equal to IL minus I naught. T on is equal to D into T plus IC off is again IL minus I naught into T off is nothing but 1 minus D into T is equal to 0. So if we solve this equation, we are going to get IL is equal to I naught. See, IL is equal to I naught means the average value of the inductor. It indicates that the average value of the inductor current is equal to output current. So the average value of the inductor current is equal to I naught. That is the meaning of this equation. So the average value of the inductor current is equal to I naught. Suppose if the load is resistive load, then I naught is equal to V naught by R. So for resistive load. See, then I am going to analyze during the turn on condition. So when the switch is on, then VL on is equal to means the voltage across the inductor during the on time, which is VL on is equal to Vs minus V naught. So during this on period, the current in the inductor is changing from IL minimum to IL maximum. So therefore, if you apply the equation voltage across the inductor and the current in the inductor is L into dIL on by dt on is equal to Vs minus V naught, which is L into the amount of change in inductance is ripple current, the amount of change in inductor current is ripple current, which is delta IL. So delta IL by the time for this is T on. So L into delta IL by T on is equal to Vs minus V naught. So L into delta IL by T on is nothing but, so dt is equal to Vs minus V naught. So therefore VL into delta IL by dt is equal to Vs minus, where V naught is called as the average value of the output voltage, which is equal to D into Vs. Just now we have got. So if you solve this equation, we are going to get delta IL is equal to D into 1 minus D into Vs by F into L. So this is the equation that you are going to get finally. So delta IL is equal to D into 1 minus D into Vs by F into L. So this is the equation that we have got when during the switch is on condition. So you can see clearly as the frequency increases, if you increase the frequency, what is going to happen? This denominator is going to get increased. So therefore overall value is going to get decreased. As the frequency increases, the change means the ripple current in the inductor is going to get decreased. So now I want to find what is the value of the maximum value of the inductor current. So maximum value of the inductor current is equal to IL average plus delta IL by 2. So IL average is nothing but I naught. So I naught plus delta IL by 2. So whatever when the switch is on, whatever the current in the inductor, the same current flowing into the switch also. So this is the same current, which is the maximum value of the switch current. Similarly, IL minimum is equal to IL average minus delta IL by 2. So IL average is nothing but I naught. So I naught minus delta IL by 2. See, whenever the switch is on, whatever the current in the inductor is the same current flowing through the switch also. So this will be the minimum current flowing through the switch. So maximum value of the maximum switch current, the maximum value of the switch current is the maximum value of the inductor current, and the minimum value of the switch current is the minimum value of the inductor current whenever the switch is on. So now I am going to assume all the devices are ideal. So therefore whatever the input power is equal to output power. So because all the devices are ideal, so no losses in the devices. So whatever the input power is equal to output power. So input power is Vs into Is is equal to V naught into I naught. So Vs average into Is average is equal to V naught into I naught. So Vs average into Is average is equal to V naught average into I naught average. So Is is equal to V naught average by into I naught average by Vs average. So Vs average is nothing but Vs, whereas V naught average is equal to D into Vs into I naught by Vs. So now Vs cancels, so we are going to get D into I naught. So listen carefully, whatever the input power is equal to output power So therefore, Vs average into Is average is equal to V naught average into I naught average. So Vs average is equal to Vs average is equal to Vs average is equal to Vs, and Is average is equal to, see, I have already told you whatever the input power is equal to output power, means no losses. So already I have assumed that all the devices are ideal, so therefore no losses in the devices. So therefore Vs average into Is average is equal to V naught average into I naught average. So the input is a DC fixed voltage, so Vs average is equal to Vs. So therefore Is is equal to V naught average into I naught average by Vs average. So V naught average is equal to D into Vs into I naught average by Vs. So Vs cancels, we are going to get D into I naught. So therefore the average value of the source current, is equal to D into I naught. So the average value of the source current is equal to D into I naught. So this is the expression that you need to remember. So the average value of the source current is equal to D into I naught. See, the switch is on only from 0 to T on. The switch is on from only 0 to T on. So T on is nothing but dt. From during the T off, the switch is open. So therefore the switch current is equal to 0 in the. So whatever the inductor current is the same current in the switch also. So therefore IL average, I am going to assume the average value of the inductor. So therefore the average value of the inductor current is the average value of the source current in this period. So therefore, see, now I want to find what is the average value of the switch current is equal to IL average into dt by capital T. So we are going to get D into IL average. So the average value of the switch current is equal to D into IL average. Similarly, the RMS value of the switch current is equal to, here IL average into under root over dt by T. So we are going to get under root over D into IL average. So this is the RMS value of the switch current, which is equal to under root over D into IL average. Similarly, I want to draw for the freewheeling diode. See, freewheeling diode is going to connect only from T on to T. So T on to T, only in this period the freewheeling diode is going to conduct. Whenever the freewheeling diode is going to conduct, whatever the inductor current is the same current flowing through the freewheeling diode. So this is IL average. So I am going to assume this is the IL average. So the freewheeling diode average value is equal to IL average into T minus dt by capital T. So you are going to get finally IL average into 1 minus D. So if you want to find what is the RMS value of the freewheeling diode current is equal to IL average into under root over T minus dt by T, you are going to get IL average into under root over 1 minus D. So this is the value of the, by this we are going to get the average value of switch current, RMS value of switch current, average value of the freewheeling diode current, and RMS value of the freewheeling diode current. So delta Q is equal to C into delta Vc. So you can see clearly that IC, see, IC is equal to positive means it is charging, but IC is equal to negative means it is discharging. See, IC is equal to positive means the capacitor is charging, and IC is equal to negative means the capacitor is discharging. So now I want to find what is the amount of charge which is present, which is equal to half into delta IL by 2. So half into delta IL by 2 into, which is T by 2, is equal to delta IL by 8F. See, I want to find how much amount of charge is present in this area. So I want to find how much amount of charge is used by this capacitor in this area. So therefore, the amount of charge is called, it's the area of the IC and T. So charge is the area under the current and time period. So therefore, the area under the current and time is called as charge. So therefore, delta Q is equal to, so delta Q is equal to, this area is half into delta IL by 2 into T by 2. So half into delta IL by 2 into T by 2. So half into delta IL by 2 into T by 2. So you are going to get delta IL by 8 into F. So delta IL by 8 into F you are going to get. So delta Vc is equal to delta Q by C. So the amount of change in capacitor voltage or the output voltage is equal to change in charge by C. So you are going to get delta IL by 8 FC. So this much amount of change in capacitor voltage or the output voltage that you are going to get. So this much amount of capacitor voltage, the amount of change in capacitor voltage or the change in output voltage you are going to get, which is delta Vc is equal to delta Q by C is equal to delta IL by 8 into FC. But I have already told you delta IL is equal to D into 1 minus D into Vs by F into L. This we just now discussed. So here in place of delta IL, if you substitute this equation, we are going to get finally delta Vc is equal to D into 1 minus D into Vs by 8 F square Lc. So this is the value of the amount of change in capacitor voltage or the change in output voltage you are going to get. See, now I want to do the derivative of this capacitor voltage with respect to D. At what D I am going to get the maximum amount of change in capacitor voltage or the output voltage. So if you do this derivative equal to 0, we are going to get at D is equal to 0.5. So at D is equal to 0.5, we are going to get a maximum amount of the change in capacitor voltage or the output voltage. So if you substitute D is equal to 0.5 in this equation, we are going to get finally the maximum value of the capacitor change in capacitor voltage is equal to Vs by 32 F square Lc. So Vs by 32 F square Lc is the maximum amount of the change in capacitor voltage or the change in output voltage for a duty ratio which is 0.5. So if the change in capacitor voltage is maximum during this period, if the change in capacitor voltage is maximum during this period which is Vs by 32 F square Lc, so similarly the change in inductor current will be also maximum. So the change in inductor current is also equal to maximum. So you know that equation, in that equation substitute D is equal to 0.5, you are going to get Vs by 4FL. So therefore the maximum value of the capacitor voltage, the change in capacitor voltage or the output voltage is maximum at D is equal to 0.5, and similarly the maximum value of the change in inductor current are going to get at D is equal to 0.5. So these are the equations that you are going to get finally. So now we are going to find what is the value of the critical inductance. Critical inductance means LC. So here minimum value of L which makes the continuous conduction from 0. So minimum value of L which makes continuous conduction from 0 means here the minimum value of inductance for which the minimum value of the inductor current will be 0. So therefore the minimum value of inductance for which the continuous conduction is possible. So the minimum value of inductance which makes continuous conduction from 0. If L is greater than this minimum value, yes, definitely continuous conduction is possible. But if the L is lesser than this minimum, means discontinuous conduction is possible. So the minimum value of L which makes the continuous conduction from 0. So therefore, for this value of minimum inductance or the critical inductance means the minimum value of inductance at which the inductor current minimum value is equal to 0 means it is going to start from the origin itself, from the 0 itself. So IL minimum is equal to 0 for LC. I have already told you IL minimum is equal to I naught, IL average minus delta IL by 2, but IL average is equal to I naught. So I naught minus delta IL by 2 is equal to 0. But I have already told you I naught is equal to, see, I naught is equal to delta IL by 2. Delta IL that we have already discussed, which is D into 1 minus D Vs by FLC. So delta L is equal to D into 1 minus D into Vs by FL. L means here we have to go for LC. So this is the equation that you are going to get. So I am going to assume the load is a pure resistive load. So I naught is equal to V naught by R. So here as the load, see, as the load is a basically it can be even very inductive load. So V naught average is equal to I naught average into R. So therefore I naught is equal to V naught average by R. So for R load, so therefore V naught by R is equal to here V naught is again V naught is equal to D into Vs by R is equal to this equation D into 1 minus D Vs by 2FLC. So if you solve Vs cancel, D cancels. So if you solve this one, we are going to get LC is equal to R into 1 minus D by 2F. Or simply if you do the rearrangement, we are going to get D is equal to 1 minus 2 LCF by R. So this is the value of the equation we are going to get. So D is equal to 1 minus 2 FLC by R. So D is equal to 1 minus 2 FLC by R. So this is the equation that you are going to get. So D is equal to 1 minus 2 FL. So 2 FL by R or simply FL. LC means is called as the critical inductance. So D is equal to 1 minus 2 FL by R. Here L means critical inductance. So this is the equation we are going to get finally. This is the critical inductance. So critical inductance means here the inductor current is going to start from 0 itself. So if the L is lesser than this critical inductance means discontinuous conduction is possible. If L is greater than this the critical inductance means continuous conduction is possible. Similarly, critical capacitance. The critical capacitance means minimum value of CC which makes output voltage just continuous or VC minimum is equal to 0 means this is the critical capacitance below which discontinuous conduction is possible for the output voltage. Similarly, if more than this means definitely continuous conduction is possible even for the output voltage or the capacitor voltage. So therefore, minimum value of CC which makes the output voltage just continuous means the minimum value of the output voltage of the capacitor voltage is equal to 0. I have already told you minimum value of the capacitor voltage is equal to V0 average minus delta Vc by 2. These things I have already told you. So therefore, Vc minimum is equal to Vc average. So Vc average minus delta Vc by 2. Vc average is nothing but V0. So V0 minus delta Vc by 2 is equal to 0. So V0 is equal to half into delta Vc. Just now we have done which is d into 1 minus d into Vs by 8f square L Cc. Here we are going to use the critical capacitor. So Cc is equal to, whereas V0 is equal to d into Vs. So if we solve this one, we are going to get Cc is equal to 1 minus d by 16f square L. So Cc is equal to 1 minus d by 16f square L. Suppose if I keep both this LCC and the critical inductance and the critical capacitance, if we keep both these equations in this one, then what is going to happen? Then Cc is equal to 1 minus d by 16f square LC. LC value just now we have figured out. If you keep that equation here and if you solve this one, we are going to get 1 by 8fr. So this is the value of critical capacitance is required for a given critical inductance. So we can say that for a given amount of critical inductance, this much amount of critical capacitance is required. So with the help of critical inductance, we can say that the minimum value of the inductor current will be equal to 0, and for a given value of the critical capacitance, the minimum value of the capacitor voltage will be always equal to 0. IL maximum means basically maximum current passing through inductor. In this case, whatever the maximum current passing through inductor will be passing through even the switch. IL minimum means minimum current passing through the inductor. In this case, in the circuit diagram, we can say that the same amount of minimum current is also passing through the switch. If the chosen inductance is greater than critical inductance, or if the chosen capacitance is greater than the critical capacitance, we can say that continuous operation is possible for both the inductor current and also the output voltage. If L is lesser than the critical inductance and C is lesser than the critical capacitance, then discontinuous operation is possible for both the inductor current and also the output voltage. I have already told you V0 is equal to d into Vs and Is is equal to d into I0. So therefore, V0 by Vs is equal to d is equal to Is by I0. So simply we can say that V0 into I0 is equal to Vs into Is. This is the basic equation. So V0 into I0 is equal to Vs into Is. So basically all these are the average values. This buck converter is also called as a step down converter. So this is basically here the average value of the output voltage is always positive. The current is always positive. So V0 is always positive and the I0 is always positive. So therefore we can say it is a class A chopper. So this is the class A chopper. So the average value of the output voltage is always positive and the average value of the output current is also positive. So it is called as the class A chopper. So this is the diagram we are going to get for a class A chopper. So therefore buck converter or the step down chopper is also a class A chopper. I have already told you the inductor current and the capacitor current. The inductor current and the capacitor current are triangular waveform. You can see from the diagram itself. Whereas the capacitor voltage or the output voltage is a sinusoidal waveform. It is like a sinusoidal waveform. So here Vc minimum is equal to Vc average minus delta Vc by 2. So Vc average is nothing but the output voltage V0 minus delta Vc by 2. Similarly, Vc maximum is equal to Vc average plus delta Vc by 2. Vc average is nothing but V0. So V0 plus delta Vc by 2. The delta L is called as the ripple current in the inductor. And delta Vc is called the ripple voltage in the output voltage or the capacitor voltage. So always the capacitor voltage is equal to the load voltage. So Vc of t is equal to V of t. where F is called as the frequency at which the switch is operated. So this is the frequency at which we are going to operate the switch. So this is all about this step down chopper or the buck converter. So now we are going to discuss about the boost converter. So boost converter is also called as the step up converter or the step up chopper. So boost converter is also called as the step up chopper. So basically we are going to learn about the continuous conduction mode. Means whatever the inductor we have taken, it is greater than the critical inductance, or whatever the capacitance we have taken, it is greater than the critical capacitance. Then only the continuous conduction is possible for this inductor current and also the capacitor voltage or the output voltage. So just we have interchanged the devices via anti-clockwise. So S, D, L. So previously here there is S, this is D and this is L. But now just we have given an anti-clockwise shift. So anti-clockwise shift we have given. So therefore S, D, L. So therefore this is the same thing which is called as the load. For load we are going to keep a capacitor because there will be no change in the output voltage. Similarly we are going to give a this supply voltage of Vs. So this is the source current Is, the inductor current is IL. This is a switch or the chopper. And this is the current in the diode which is I1. And this is the current in the capacitor which is IC, and the current in the load is I0. And this is the voltage across the load or across the resistor which is RV0. So now I have already told you for 0 to T on we are going to close the switch or on the switch. After T on to T, means during the T off we are going to open the switch or turn off the switch. Then we are going to analyze what is the waveforms of each and every aspect we are going to see. So whenever the switch is on, you can see clearly the inductor is going to become charged. So the inductor current is going to rise. So from IL minimum to IL maximum. So IL minimum to IL maximum. But when the switch is open, so whatever the energy stored by the inductor is going to release. So therefore the current is going to get decay because it is going to discharge. Let me assume the ripple in the inductor current is delta IL. So here the IL average is going to lie exactly between this IL minimum and IL maximum. This IL average. So therefore we can say that IL minimum is equal to IL average is minus delta IL by 2, and IL maximum is equal to IL average plus delta IL by 2, because it is going to lie exactly between them. So therefore this is delta IL by 2 and this is delta IL by 2, but the overall ripple is delta IL. So now we are going to analyze furthermore. I already told you the switch, the source and the inductor are in series. So therefore always the source current is equal to inductor current because the source and the inductor are in series. So therefore whatever the source current is always equal to the inductor current for the all time. So therefore simply we can say that the source current average value is equal to inductor current average value. So when the switch is on, the VL, the voltage across the inductor during the switch is on. So VL on is equal to supply voltage which is Vs, and also the source current is equal to inductor current when the switch is on. And so simply we can say that here now, so when the switch is on, the diode is off. So therefore by applying the KCL we are going to get IC plus I0 is equal to 0 because diode D is off. So therefore I1 is equal to 0 because diode D is off. So simply we can say that I0 is equal to minus IC on. So L is charging in this condition. I have already told you I am going to assume that I0 is a constant value. The load current is a constant value, and I have also assumed that the L and C which are larger than the critical inductance and the critical capacitance. Then only continuous conduction is possible for the inductor current and also the output voltage of the capacitor voltage. So when the switch is off, what is going to happen? When the switch is off, it is open. So the source current is always equal to the inductor current. Now the inductor is going to discharge its energy to the load. So therefore current will decay. Now the diode is under the conduction mode. So if you apply the KVL, which is plus Vs minus VL of minus V0 is equal to 0. So VL off is equal to Vs minus V0. So IC off is equal to So now IC off is equal to, because now it is now the diode is connecting, so therefore IL is equal to IC plus I naught. So IC on is equal to IL minus I naught. L is discharging. So I already told you now the source current is equal to inductor current is equal to diode current, which is I1. So now we are going to apply the basic principle, which is the average voltage across the inductor will be always equal to 0. So VL on into T on plus VL off into T off is equal to 0. So VL on is equal to Vs, T on is equal to D into T plus VL off is equal to, so VL off is equal to Vs minus V naught into T off is equal to 1 minus D into T is equal to 0. So if we analyze the circuit, we are going to get the average value of the output voltage is equal to Vs by 1 minus D. So the average value of the output voltage is equal to Vs by 1 minus D. I have already told you D is going to lie between 0 to 1. So therefore the average value of the output voltage is always greater than the supply voltage. That is the reason we call this as the boost converter or the step up chopper. And I have already told you for capacitor, the average value of the capacitor current is always equal to 0. So IC on into T on plus IC off into T off is equal to 0. But IC on is equal to minus I naught. T on is equal to DT plus IC off is equal to IL minus I naught into T off is equal to 1 minus D into T is equal to 0. So if we solve this one, we are going to get IL average is equal to I naught by 1 minus D. So the average value of the inductor current is equal to I naught by 1 minus D. So IL average is equal to, in this case, which is I naught by 1 minus D. So the average value of the inductor current in this case, which is I naught by 1 minus D. So now I am going to draw the capacitor current. I have already told you whenever the switch is on, so whenever the switch is on, the capacitor current is equal to minus I naught. But whenever the switch is open, whenever the switch is open, IC is equal to IL minus I naught. IL value we know. IL value is just this decay. From that we have to remove the I naught. From that we have to remove the I naught. So if you remove the I naught, we are going to get in this format. So we are going to get in this format we are going to get. So always the capacitor voltage is going to go from maximum value to minimum value, like fluctuation, like a sinusoidal waveform, it is going to be occur. So VC maximum, VC minimum, this is VC average. So this is overall, this ripple is called as a delta DC. So I1 is called as a diode in the current in the diode. So here, whenever the switch is on, the diode current is equal to 0. So I1 is equal to 0. But whenever the switch is off, whatever the source current is equal to inductor current is equal to I1. So inductor current in this range is like this. So therefore this is the value from IL maximum to IL minimum. So whatever the current in the inductor in this period, it will be same in the field diode also. So this is the range. So we can say that the diode current is like a trapezoidal waveform, whereas the inductor current is a triangular waveform. During the on condition, whenever the switch is on, VL on is equal to Vs. So VL on is equal to, in this range, the current is changing from IL minimum to IL maximum. So L into the amount of changes delta IL by T on is equal to Vs. T on is equal to dt. So if you solve this one, we are going to get the amount of change in, or the ripple current is equal to delta IL is equal to D into Vs by F into L. So this is the change in ripple current, or change in the order of the change in the electric current we are going to get, which is delta L. I have already told you LL maximum is equal to IL maximum is equal to IL average plus delta IL by 2. But IL average just now we have got, which is I naught by 1 minus D plus delta IL by 2. Whereas IL minimum is equal to IL average minus delta IL by 2. IL average is equal to I naught by 1 minus D minus delta IL by 2. So by this we are going to get the maximum value of the inductor current and also the minimum value of the inductor current. Whatever the maximum value of the inductor current is the maximum value of the source current. Whatever the minimum value of the inductor current will be the minimum current of the source current. And also this maximum current is going to flow through the switch also. And also this minimum current is also going to flow through the switch current. So the minimum value, the maximum value of the current which is flowing to the switch is IL max, and the minimum value of the current which is flowing to the switch is IL minimum. because in the on position, the switch is on, the current is moving from IL minimum to IL maximum. So this is also equal to switch current. So I have already told you whatever the input power is equal to output power, because all the devices which we have assumed are ideally lossless, means they are not going to consume any power. So therefore whatever the input power is equal to output power. So input power is equal to Vs average into Is average is equal to V naught average into I naught average. So Vs average is Vs and Is average is Is. Just we are going to write, because it's a DC supply, so therefore this is a Vs. So Is average is equal to V naught into I naught. So therefore Is is equal to V naught I naught by Vs. So here I have already told you, which is V naught is equal to, so V naught is equal to Vs by 1 minus d. So Vs cancels, we are going to get I naught by 1 minus d. So therefore the average value of the source current is equal to I naught by 1 minus d. So you can say clearly the average value of the inductor current is equal to the average value of the source current is equal to I naught by 1 minus d. This we have already discussed. So the average value of the source current is equal to average value of the inductor current is equal to I naught by 1 minus d. Whereas I naught is equal to, the I naught is equal to, suppose for pure resistive load or the RL load also, I naught is equal to V naught average by R. So now we are going to find what is the current in the switch. See, switch current, see the average value of the inductor current is going to flow. Whenever the switch is on, whatever the inductor current, it is blindly flow to the switch. So therefore IL average is going to get flow only for 0 to T on or dt. After the switch is open, so therefore current here in the switch is equal to 0. So this is the current we are going to get. Similarly, I want to find what is the current in the diode. So diode, when the switch is on, diode current is equal to 0. But when the switch is off, whatever the inductor current is flowing to the diode, so IL average is going to flow only through the T off period, which is into T. So we are going to find what is the average value, RMS value of each and everything we are going to figure out. I have already told you IL average is equal to Is average is equal to I naught by 1 minus d. So therefore the average value of the switch current, is equal to IL average into dt by t. So IL average into dt by t, you are going to get, which is d into IL average. So the average value of the switch current is equal to d into IL average. Whereas IL average is equal to I naught by 1 minus d. So finally you are going to get like this. So the switch current average value is equal to d into I naught by 1 minus d. Whereas the switch current RMS value is equal to same thing, IL average into under root over dt by t, which is root d into IL average. Root d into IL average is I naught by 1 minus d. So this is the RMS value of the switch current. Similarly, I want to find what is the diode current average value is equal to IL average into, which is from dt to t. So therefore t minus dt by t, you are going to get finally 1 minus d into IL average. IL average is nothing but d I naught by 1 minus d. So 1 minus d cancels, we are going to get I naught. So the average value of the diode current is equal to I naught, because you can see clearly the average value of diode current is equal to I naught, because the average value of the capacitor current is equal to 0. That is the reason. So IDRMS is equal to IL average into under root over t minus dt by t. You are going to get finally IL average into 1 minus d. But IL average is equal to I naught by 1 minus d. You can substitute here and you can substitute and you can do the simplification. See, during on tension, whenever the switch is on, the capacitor is going to deliver power to load. So therefore capacitor is discharging. See, whenever the switch is on, what is going to happen? The freewheeling diode is off. So whatever the charge in the capacitor, it is going to deliver to the load. So therefore capacitor is discharging. So in this condition, what is going to happen? IC is equal to minus I naught. This we have already discussed. So IC is nothing but capacitor current. It is going to change, which is C into dV by dt is equal to minus I naught. So C into dV by dt is equal to minus I naught. So dV is equal to minus I naught by C into dt. So I want to do the integration, because the capacitor is discharging. The capacitor is discharging means the voltage is going to decrease from maximum value to minimum value. So integration of from maximum value to minimum value is equal to integration of t is equal to 0 to t is equal to dt. Only in this term and time. So therefore t is equal to 0, its value is maximum value. At t is equal to dt, its value is minimum value. So therefore, integration of maximum value to minimum value dv is equal to integration of t is equal to 0 to t is equal to dt minus I naught by c into dt. So if you do the simplification, v minimum minus v maximum is equal to minus I naught by c into dt. So this is called as the, see, v minimum minus v maximum is nothing but minus delta vc, because delta vc is the maximum value minus minimum value. So minus delta vc is equal to minus I naught by c into dt. So minus minus cancels, we are going to get delta vc is equal to d into I naught by f into c. So this is the amount of change in the output voltage or the capacitor voltage we are going to get, whereas delta vc is called as the maximum value minus minimum value of the output voltage or the capacitor voltage. I already told you I naught is equal to v naught by r. So I naught is equal to v naught by r means v naught is equal to vs by 1 minus d. So if you substitute v naught is equal to vs by 1 minus d, so you are going to get this expression. So you can say clearly the delta Vc is equal to d into I naught by Fc. Just now we have seen. So therefore delta Vc is directly proportional to d. As d increases, delta Vc is also goes on increases. So now we are going to find what is the critical inductance and the critical capacitance. Critical inductance means there is a continuous conduction, just continuous conduction in the inductor current. So therefore IL minimum is equal to 0. Means the current is going to start from 0 value. So IL minimum is equal to 0. So therefore IL minimum is IL average minus delta IL by 2 is equal to 0. So but IL average is equal to I naught by 1 minus d is equal to half into delta IL just now we have shown, which is 3 Vs by f into LC, because LC is called the critical inductance. Now we are going to see. So whereas I naught is equal to, just now I told you, I naught is equal to V naught by R, whereas V naught is equal to Vs by 1 minus d. So therefore you are going to get in this fashion. So therefore I naught is equal to V naught by R. So I naught is equal to V naught by R. So I naught is equal to V naught by R into 1 minus d is equal to half into dVs by FLC. Whereas V naught is equal to Vs by 1 minus d into R into 1 minus d is equal to dVs by 2 FLC. So Vs cancels, we are going to get finally the value of critical inductance is equal to d into 1 minus d whole square into R by 2f. So this is the value of the critical inductance you are going to get, which is d into 1 minus d whole square into R by 2f. Similarly, I want to find what is the value of the critical capacitance. Critical capacitance means just minimum continuous conduction in the capacitor voltage or the output voltage. Means the capacitor voltage or the output voltage is going to rise from 0 value. So therefore Vc minimum is equal to 0. So Vc minimum means Vc average minus delta Vc by 2 is equal to 0. So therefore Vc average is equal to delta Vc by 2. Vc average is called as the output voltage average value. So V naught is equal to half into delta Vc, just now we have saw, which is I naught into d by Fc. This we have just now discussed. So I naught into d by Fc. So here V naught is equal to half into I naught is equal to V naught by R, d by Fc. So V naught cancels. So we are going to get the critical capacitance is equal to d by 2fr. You can see clearly the critical capacitance is independent of the inductance. So this is the value of the critical inductance and this is the value of the critical capacitance. If whatever the value of the inductor and capacitor which are greater than these values, then there is continuous conduction in the inductor current and also in the capacitor voltage. So IL maximum means maximum current passing through inductor. IL maximum means basically maximum current is passing through the inductor. IL minimum means minimum current passing through inductor. In this case, whatever the maximum value in the conductor is the maximum value of the source current. Whatever the minimum value of the inductor current is the minimum value of the source current. Similarly, whatever the maximum value of the inductor current is the maximum value of the current which is flowing to the switch, and also whatever the minimum value of the inductor current is the minimum value of the current which is flowing to the switch also. I have already told you the current IL is in the triangular waveform and the average value of the inductor current is equal to the average value of the source current is equal to I naught by 1 minus d, and V naught is equal to Vs by 1 minus d, and Is average is equal to I naught by 1 minus d. So if you solve this one, we are going to get V naught by Vs is equal to 1 by 1 minus d is equal to Is by I naught. And I have already told you the average value of the capacitor voltage is equal to output voltage average value, which is equal to Vs by 1 minus d. And the average value of the inductor voltage will be always equal to 0, and the average value of the capacitor current is always equal to 0. This thing I've already told you, the switch current RMS value. The switch current RMS value, just now we have solved, it is IL average into under root over dt by t. So dt cancels, we are going to get IL average into root t. So IL average is called as the source current average value, both are equal. So root d into IS average. So IS average is equal to input power by supply voltage. So input power by supply voltage. So simply root d into input power by supply voltage, you can write either in this format also. I have already told you the average value of the output voltage is equal to Vs by 1 minus d, where d is equal to T1 by t. So if you substitute here, you are going to get finally Vs into t by t off. So if you know t and t off, you can substitute and you can get the value of the V naught. Non-conducting time of thyristors means conducting time of the thyristor chopper. Conducting time of the thyristor chopper, which is T off. On time of thyristor chopper means T off. So you have to listen this one. See, non-conducting time of thyristor. Non-conducting time of thyristor means the conducting time of the thyristor chopper, which is T off. On time of thyristor chopper means it is a T off. This is a thing that you need to remember. So on conducting time of non-conducting time of thyristor is equal to conducting time of thyristor chopper is equal to T on. On time of thyristor chopper is equal to T off. So these are the things that you need to remember. So non-conducting time of thyristor is equal to conducting time of thyristor chopper is equal to T on. On time of thyristor chopper is equal to T off. With this we have completed the step-up chopper or the boost chopper. So now we are going to discuss about the buck boost converter. So basically we are going to learn about the continuous conduction mode. Buck boost converter, we are going to learn about the continuous conduction mode. So this is the circuit diagram of this buck boost converter. So in the buck converter, this is S, this is D, this is L. Whereas in the boost converter, just you have to do the anti-clockwise shift. So S, D, L. But now for the buck converter, just you have to interchange the D and L. So D and L you have to interchange. Therefore, if you keep the diode, it will be like this. Just again you have to interchange the diode. So you are going to get in this format. So this is the actual buck boost converter circuit. So this is the load resistor you have to always keep a capacitor. So therefore, the change in voltage will be very much less. So this is the supply voltage Vs and the supply current is Is. So this is the supply current Is. So this is the supply current Is. So this is the inductor. So therefore, the inductor voltage is plus or minus VL. So inductor voltage is plus or minus VL and the inductor current is IL. This is the switch. So this is the capacitor. So this is the capacitor. So capacitor voltage is plus or minus. So from upper it is plus and it is down is negative. So this is the capacitor voltage and this is the capacitor current IC. So this is the load current I0. So this is the capacitor current IC. This is the capacitor voltage plus and minus V0, VC, and also the output voltage is plus or minus V0 and this is the output current I0. So we have to assume that I0 is a constant value. Means we have to assume that the I0 is a constant value, and also I have already told you that whatever the chosen inductors and capacitors should be always greater than the critical inductance. Then only continuous conduction is possible. So now we are going to basically analyze this circuit. So this is a switch. So switch we are going to on during 0 to T on, we are going to on the switch, and from T on to T on T we are going to have the switch. So we are going to repeat this process after a time period of T. So we are going to see what is the nature of this one. So whenever the switch is on, so therefore the supply voltage is equal to inductor voltage. So the inductor is going to get charged from minimum value to maximum value. So IL minimum to IL maximum is going to get charged. Whereas from dt to T, the switch is off. So whenever the switch is off, this inductor is going to deliver its energy to the load. So therefore its current will decay. It will decrease. So from IL maximum to IL minimum, it is going to decrease. The amount of ripple is delta IL. So this is IL average. So the average value is going to lie exactly between these two things. So therefore, IL average is equal to, it is IL average, say IL maximum is equal to IL average plus delta IL by 2, and IL minimum is equal to IL average minus delta IL by 2. So this is the thing that you are going to get from these graphs. So now we are going to basically analyze this circuit. I have already told you during the on position. So during the on position, the switch is on and the diode is off. So therefore, whatever the supply voltage is the voltage across the inductor. So VL on is equal to Vs So VL on is equal to Vs, and IC on is equal to, because the diode is open, so therefore IC on is equal to minus I naught. So and the inductor is in charging condition. Whereas when the switch is off, when the switch is off, the diode is on, so therefore inductor is going to discharge its energy into load. So inductor is discharging. So therefore VL off is equal to, so VL off is equal to, if you apply KVL, you are going to get VL off is equal to V naught. So VL off is equal to V naught. You can see clearly. And IC off is equal to, see IC off is equal to, if you apply the KCL, we are going to get IL plus IC plus I naught is equal to 0. So therefore IC is equal to minus of IL plus I naught. So IC off is equal to minus of IL plus I naught. And the inductor is discharging. So now I am going to apply the average value of the inductor voltage is always equal to 0. So VL on into T on plus VL off into T off is equal to 0. Whereas VL on is equal to Vs, T on is a dt plus VL off is equal to V naught into 1 minus d into T is equal to 0. So if you solve this one, we are going to get V naught is equal to minus d Vs by 1 minus d. So now the sign convention is always you need to remember. So therefore V naught is equal to minus d Vs by 1 minus d. So overall the upper part is positive, the down part is negative. So therefore V naught is equal to minus d Vs by 1 minus d. Otherwise, if you take down part as positive and the upper part is negative, then it will be d into Vs by 1 minus d. So but you have to take this convention, which is the upper part is always positive and the down part is always negative. So therefore V naught average is equal to minus d Vs by 1 minus d. And I am going to apply the average value of the capacitor current is always equal to 0. So IC1 into T1 plus IC off into T off is equal to 0. So IC1 is equal to minus I naught, T1 is equal to dt, whereas IC off is equal to minus of IL plus I naught, and T off is equal to 1 minus d into T is equal to 0. So if we solve this equation, we are going to get IL average is equal to minus I naught by 1 minus d. So therefore the average value of the inductor current is equal to minus I naught by 1 minus d. So minus I naught by 1 minus d you are going to get. So when switch is on, we can see that the inductor voltage is equal to supply voltage. So VL on is equal to Vs. So therefore VL on is equal to L into delta IL by the amount of change delta IL by T on dt is equal to Vs. So if you solve this one, we are going to get delta IL is equal to dVs by F into L. The maximum value of the inductor current is equal to IL average plus delta IL by 2. But IL average we have discussed that now, which is minus I naught by 1 minus d plus delta IL by 2. See V naught, I naught we can also call, I naught is nothing but V naught by R. So V naught by R, we can replace I naught by V naught by R, same thing. Whereas IL minimum is equal to IL average is minus delta IL by 2, IL average is minus I naught by 1 minus d minus delta IL by 2, whereas I naught is equal to V naught by R. So we are going to get these expressions. See the maximum value of the inductor current is also going to flow through switch. So the maximum value of the inductor current is equal to maximum value of the switch current, whereas the minimum value of the inductor current is also equal to minimum value of the switch current. I have already told you the input power is always equal to output power, because whatever the devices we have taken, they are ideal, so no losses in there. So Vs into Is is equal to V naught into I naught. All these are the average values. So Is is equal to V naught into I naught by Vs. So this is the equation we are going to get. So now I want to draw the switch current and also the diode current. See, whenever the switch is on, you can see clearly, whenever the switch is on, you can see clearly whatever the inductor current is also flowing through the switch. So therefore, you can see clearly from 0 to dt. So from 0 to dt, it is going to get on. So therefore, this is IL average. Whatever the average value of the inductor current is also flowing through the switch. Whenever the switch is open, its current is equal to 0. So therefore, the average value of the switch current is equal to IL average into dt by d. We are going to get d into IL average. Similarly, the RMS value of switch current is equal to IL average into under root 2 of dt by t. Dt cancels, we are going to get root d into IL average. And similarly, if you want to find what is the diode current average value. See, during the switch is on, the diode is off, so its current is 0. Whereas from dt to t, the switch is off, so therefore, whatever the inductor current is also flowing to the diode current, so therefore, IL average is going to flow in this manner. So this is the thing we are going to get. So the average value of diode current is equal to IL average into T minus dt by T, you are going to get 1 minus D into IL average. Similarly, the RMS value of the direct current is equal to, which is IL average into under root of T minus dt by T. Dt cancels, we are going to get IL average into under root over 1 minus D. So during on position, whenever the switch is on, the freewheeling diode is off. So therefore the capacitor is going to deliver its energy to the resistor. So its voltage is going to get decreased. So during on, C is delivering power to load. So therefore its voltage is going to get decreased from maximum to minimum. So in that condition, the IC on is equal to minus I naught. IC on is nothing but C into dVc by dt is equal to minus I naught. So dVc is equal to minus I naught by C into dt. So it is going from maximum to minimum value. So maximum to minimum dVc is equal to from 0 to dt minus I naught by C into dt. So if you solve this one, we are going to get finally delta Vc is equal to D into I naught by Fc. Delta Vc is called as a maximum value minus minimum value, Vmax minus V minimum. So you can say clearly delta Vc is directly proportional to D. As the D increases, delta Vc also goes on increases. So now I want to find what is the value of the critical inductance and also critical capacitance. Critical inductance means there is a just minimum continuous conduction in the inductor current, means the inductor current is going to rise from 0. So therefore IL minimum is equal to 0. IL minimum, just now I have told you, is IL average minus delta IL by 2. So therefore IL average is equal to delta IL by 2, but IL average is equal to minus I naught by 1 minus D is equal to half into delta IL, just now we have saw D into Vs by F into LC. So what is the value of I naught? I naught is equal to V naught by R. So V naught by R, whereas V naught is equal to, again V naught is equal to minus D into Vs by 1 minus D. So finally you are going to get dVs by R into 1 minus D whole square is equal to half into dVs by FLC, because minus minus cancels. So now if you solve this equation, finally the critical inductance is equal to R into 1 minus D whole square by 2F. So this is the value of the critical inductance. See, if the value is more than this, is continuous conduction is always possible. Otherwise, if whatever the chosen inductance is less than critical inductance means there is no continuous conduction is possible. So now we are going to discuss about the critical capacitance, means CC. Means there is a just minimum continuous conduction in the capacitor voltage or the output voltage. So the capacitor voltage is going to rise from 0. So Vc minimum is equal to 0. Vc minimum means Vc average minus delta Vc by 2 is equal to 0. So therefore Vc average is equal to delta Vc by 2. Vc average is also equal to the output voltage. So V naught is equal to half into delta Vc, just now we have shown d I naught by F into C. So therefore here half into d V naught I naught is equal to V naught by R. So V naught by R into F into C. So if you solve this one, we are going to get finally the critical capacitance is equal to D by 2FR. So this is the value of the critical capacitance. If the value of the C is greater than this critical capacitance, there is a continuous conduction in the capacitor voltage. Otherwise, there is no continuous conduction. So if whatever the chosen inductance is greater than critical inductance and whatever the chosen capacitance is greater than the critical capacitance, then continuous operation is possible for both the inductor current and also the capacitor voltage. But if the value of the chosen inductor is less than the critical inductance and the chosen value of the capacitance is less than critical capacitance, then there is discontinuous operation in both the inductor current and also in the capacitor voltage. IL maximum means the maximum current which is flowing through the inductor, and IL minimum means the minimum current which is flowing through the inductor. Whatever the maximum value of the current which is flowing through the inductor is also the maximum value of the current which is flowing through the switch, and also it is a maximum value of the source current also. Whatever the minimum value of the current which is flowing through the inductor means it is a minimum value of the current to the switch, and also it is a minimum value of the source current. I already told you the inductor current waveform is a triangular waveform. So therefore, if you want to find what is the peak value of the switch current, what is the peak value of the switch current? The peak value of the switch current is nothing but, which is if you apply the KVL, we are going to get Vs minus V naught. Vs minus V naught is called as the peak value of the switch current, Vs minus V naught. So Vs, whereas V naught is equal to minus dVs by 1 minus d. So finally you are going to get Vs plus dVs by 1 minus d. So this is the peak value of the switch voltage we are going to get. And I have already told you the maximum value of the inductor current is the maximum value of the current which is flowing to the switch, and also the minimum value of the inductor current is the minimum value of the current which is flowing to the switch. Now basically we are going to compare all the buck converter, boost converter and the buck boost converter. So each and everything now we are going to discuss. The average value of the output voltage in the buck converter is dVs in the boost converter, which is Vs by 1 minus d, whereas in the buck boost converter, which is minus dVs by 1 minus d. Whereas IL average is equal to I0 in buck converter, which is I0 by 1 minus d in the boost converter, minus I0 by 1 minus d in the buck boost converter. And the delta IL is equal to d into 1 minus d Vs by FL in the buck converter, d into Vs by FL in the boost converter, d into Vs by FL in the buck boost converter. IL maximum is equal to IL average plus delta IL by 2 in the buck converter, IL average plus delta IL by 2 in the boost converter, IL average plus delta IL by 2 in the buck boost converter. Similarly, IL minimum is equal to IL average minus delta IL by 2 in the buck converter, IL average minus delta IL by 2 in the boost converter, IL average minus delta IL by 2 in the buck boost converter. The average value of the switch current in the buck converter, which is D into IL average, whereas the average value of the switch current in the boost converter, which is D into IL average. Similarly, the average value of the switch current in the buck boost converter is D into IL average. Whereas the RMS value of the switch current, the RMS value of the switch current in the buck converter, which is root D into IL average. Similarly, in the boost converter, which is root D into IL average. Similarly, in the buck boost converter, which is root D into IL average. Whereas the freewheeling diode current average value in the buck converter, which is 1 minus D into IL average, in the boost converter, which is 1 minus D into IL average, in the buck boost converter, which is 1 minus D into IL average. Whereas the RMS value of the freewheeling diode current in the buck converter, which is under root over 1 minus D into IL average, in the boost converter, which is under root over 1 minus D into IL average. Similarly, in the buck boost converter, which is under root over 1 minus D into IL average. The amount of change in capacitor voltage or the output voltage in the buck converter, which is D into 1 minus D Vs by 8 F square LC, in the boost converter, which is D I0 by FC, in the buck boost converter, which is D I0 by FC. The average value of the capacitor voltage is equal to V0 in buck converter, V0 in the boost converter, V0 in the buck boost converter. The critical value of the inductance in the buck converter, which is R into 1 minus D by 2F, whereas in the boost converter, which is D into 1 minus D whole square by R into R by 2F, whereas in the buck boost converter, which is R into 1 minus D whole square by 2F. If you want to find what is the critical capacitance in the buck converter, which is 1 minus D by 16F square L, in the boost converter, which is D by 2FR, whereas in the buck boost converter, which is D by 2FR. So this is a comparison of each and every parameter with respect to boost converter, buck converter, boost converter, and also the buck boost converter. So now basically we are going to study about the buck converter in the discontinuous conduction mode. Up to now we have learned about the continuous conduction mode, but now we are going to learn about the buck converter in the discontinuous conduction. Means whatever the inductance we have taken is lesser than the critical inductance, then we can say that yes, the circuit is going to operate in the discontinuous conduction mode. So this is the buck converter circuit. So buck converter circuit is just I already told you SDL. So SDL, this is the circuit diagram. So this is the supply voltage, this is the load. For the load we are going to keep a capacitor in order to vary the reduction in the capacitor voltage or the output voltage. This is plus or minus V0, and the capacitor current is IC, and the load current is I0, and the switch current is ISW, and the source voltage is Vs, and this is also source current. Source current is also equal to switch current. And this is the freewheeling diode current, which is ID, and this is the inductor current IL, and this is the voltage across the inductor VL. So now whatever the chosen inductance is lesser than the critical inductance, then we are going to analyze the circuit of waveforms. See, the switch is on. For 0 to T on means dt, we are going to on the switch. Whenever the switch is on, so therefore freewheeling diode is off, so therefore capacitor is going to get charged. So capacitor is going to charge means the inductor current is going to rise from 0 to some IL maximum. It is going to rise. And also the switch current is also equal to inductor current whenever whenever the switch is on, therefore it is going to follow the inductor current from 0 to IL maximum. This is the meaning of this one. So the diode is off in that region, so therefore the current is 0. Whereas during dt, during d to t, the switch is off, the switch is open, so therefore the inductor is going to discharge its energy into the load, so current is going to decay. So current is going to decay very faster, so therefore it is going to decay very faster within a time lesser than t, so therefore it is going to decay very faster. So whenever the switch is open, the current is equal to 0. The current is equal to 0 in the period. As the diode is going to connect, in this region, so therefore the inductor current is equal to diode current. So whatever the diode current will be same as the inductor current. So whatever the inductor current is same as the diode current in this region. So therefore this I am going to assume this is beta t. So within beta t only it is going to become 0. So this is called as the amount of change in ripple current. This is also change in ripple current, and this is also change in ripple current of delta IL. So now we are going to analyze this circuit. So during on time, what is going to happen? During on, the diode is off. So we can simply say that the inductor voltage VL on is equal to Vs minus V0. So Vs minus V0. So T on is equal to D into T. Similarly, during off position, so during the off position means the switch is open. So therefore, if you apply KVL, we are going to get VL is equal to minus V0. So VL off is equal to minus V0, and T off. See, now only for small amount of time, which is here beta t minus dt. So this is the time T off, which is only beta t minus dt, because T is take common, beta minus d into T, where beta is always lesser than 1. So beta is always lesser than 1. So therefore beta minus d into T. So now I am going to apply the voltage second balance of this inductor voltage. Means the average value of the inductor voltage is 0. So VL on into T on plus VL off into T off is equal to 0. Here VL on is nothing but Vs minus V0 into T on is nothing but Dt, and VL off is equal to minus V0 into T off is nothing but here beta minus D into T is equal to 0. So if you solve this one, we are going to get V0 is equal to D Vs by beta. Whereas in the continuous conduction mode, the average value of the output voltage is equal to D into Vs. Whereas in the discontinuous conduction mode, the average value of the output voltage is D into Vs by beta, where beta is always lesser than 1. So as the beta is lesser than 1, so simply we can say that the average value of the output voltage in the discontinuous conduction mode is always greater than the average value of the output voltage in the continuous conduction mode. So this is the thing that you need to analyze. So what is the procedure to check the circuit whether this is the discontinuous conduction mode or not? So what is the procedure to check whether the circuit is in the discontinuous conduction mode or not? I already told you the average value of the output voltage in the discontinuous conduction mode is dVs by beta, whereas the average value of the output voltage in the continuous conduction mode is d into Vs. So this value is greater than this value. So therefore the average value of the output voltage in discontinuous conduction mode is always greater than the average value of the output voltage in the continuous conduction mode. And whatever the given inductance is lesser than the critical inductance, or we can even say whatever the given inductance in the circuit is lesser than the critical inductance, then also discontinuous conduction is mode. So out of these two methods, you can opt for any method, and you can confirm that yes, discontinuous conduction is possible. The critical inductance is equal to R into 1 minus D by 2F for buck converter, R into 1 minus D whole square D by 2F for boost converter, whereas R into 1 minus D whole square by 2F for the buck boost converter. So these three formulas that you need to remember. The critical value of the inductance is equal to R into 1 minus D by 2F for buck converter, R into 1 minus D whole square into D by 2F for boost converter, R into 1 minus D whole square by 2F for buck boost converter. So now we are going to apply the power balance, which is output power is equal to input power, because we are going to assume all the devices are ideal. So therefore V0 I0 is equal to Vs Is. So basically all these things are the average values. So therefore V0 I0 is equal to Vs into Is average. So Is average is equal to V0 I0 by Vs. So now here I want to find what is the average value of this one. See, average value of the source current. The average value of the source current is equal to the average value of the switch current. The average value of the source current is equal to the average value of the switch current. So therefore from the graph we can see the average value is equal to half into delta IL into dt by T. So dt cancels, you are going to get delta IL into d by 2. So this is the average value of the source current. So therefore the average value of the source current is, you can apply by any of this formula. So delta IL by 2, delta IL into d by 2. And also the load current IL of t is equal to IC of t plus I0 of t. So therefore here now we are going to apply the average on each and every side. So therefore the average value of the inductor current is equal to the average value of the output current is equal to I0. whereas the average value of the capacitor current is always equal to 0. So therefore, I0 is equal to IL average is equal to I0 average. Therefore, I0 is equal to I0 average is equal to IL average. So the average value of the inductor current is equal to the average value of the output current is equal to I0. So if you want to find what is this value I0, so therefore the average value of the inductor current. So if you try to apply this one, which is half into delta IL into which is beta t by t cancels, we are going to get delta IL into beta by 2. So this is called as the average value of the output current or the average value of the inductor current, which is equal to I0, because the average value of the capacitor current is always equal to 0. So therefore the I0 is equal to delta IL into beta by 2. Suppose if I assume the load, suppose I am going to assume the load is pure resistive, so assuming R load, then what I am going to get? If I assume the load is resistive load, then I am going to get a relation which is beta square minus d beta minus 2L by RT is equal to 0. So beta square minus d beta minus 2L by RT is equal to 0. So if you apply this formula, ax square plus bx plus c is equal to 0, the roots beta is equal to b plus root over d square plus 8L by RT by 2. So if you remove this equation, you can get this equation, which is beta square minus d beta minus 2L by RT is equal to 0, means beta is equal to b plus root over d square plus 8L by RT by 2. So this is the important relation you need to remember. So during switch on, during the switch on, we can say that the inductor voltage is equal to L into change is delta IL by dt. Inductor voltage during the switch is on means Vs minus V0 is equal to L into delta IL by dt. So therefore now Vs minus V0 is nothing but dVs by beta is equal to L into delta IL by dt. So if you solve this on equation, we are going to get delta I is equal to Vs minus dVs by beta into dt by L. So this is the change in the ripple current or the change in the inductor current we are going to get. So now we are going to learn about the boost converter in a discontinuous conduction mode. So now just we have to do the interchange of the SDL in the anti-clockwise. So SDL. So this is the thing that you have to do the interchange with respect to buck converter. So SDL. So the input voltage is the supply voltage and the output is the load. We are going to connect the capacitor in order to reduce the amount of change in the capacitor voltage or the load voltage. So this is the supply voltage and this is the inductor current IL. The inductor voltage is plus or minus VL, and this is the switch current ISW, and this is the diode current ID, and this is the capacitor current IC, and this is the output current I0, and this is the output voltage plus or minus V0. So always the value of L is lesser than the critical inductance. Means whatever the truth inductance is always lesser than the critical inductance. Then only a discontinuous conduction mode is possible. So now we are going to analyze the graphs. So switch is on only from 0 to T on. So or simply we can 0 to DT. So whenever the switch is on, the diode is off. So therefore the inductor current is going to rise from 0 to IL maximum. So the switch current is equal to inductor current in this case. So it is going to follow the inductor current. In that case, diode is off. So therefore current is equal to 0. Whereas from DT to T, in this period only, the switch is off. So whenever the switch is off, we can say that the inductor is going to discharge its energy to the load. Or simply we can say that the diode is conducting. So therefore, the inductor current is going to decay very faster. So because of that, for some amount of time the current is 0, because it is called as a discontinuous conduction mode. So therefore, whenever the switch is open, so the switch current is equal to 0, whereas whenever the switch is open, diode current is equal to inductor current. It is going to follow the inductor current nature. So within dt only it is going to become 0. The ripple is called as a delta IL. So we are going to basically analyze these graphs. So we are going to analyze the graphs. So during on time, so during the chopper is on or during the switch is on, we can say that the voltage across the inductor is equal to source voltage and the T on is equal to D into T. Whereas during the off time, during the switch is open, so VL off is equal to Vs minus V0 and T off is equal to Bt minus Dt, which is beta minus D into T. So now we are going to apply the voltage second balance, means the average value of the inductor voltage is always equal to 0. So therefore VL on into T on plus VL off into T off is equal to 0. VL on is equal to Vs, T on is equal to Dt plus VL off is equal to Vs minus V0 and d of is equal to beta minus d into t is equal to 0. So if you solve this one, we are going to get b naught is equal to beta into ds by beta minus d. So therefore the average value of the output voltage in the boost converter in the continuous conduction mode is Vs by 1 minus d, whereas in the discontinuous conduction mode the average value of the output voltage is beta into ds by beta minus d. So this is the important relation that you need to always remember. So beta is always lesser than 1. So therefore we can say that the average value of the output voltage in the discontinuous conduction mode of boost converter is always greater than the average value of the output voltage in the boost converter in the continuous conduction mode, because beta is less than 1. So therefore, what is the procedure to check whether the circuit is in the discontinuous conduction mode or not? So whatever the average value of the output voltage in the discontinuous conduction mode is always greater than the average value of the output voltage in the continuous conduction mode. The average value of the output voltage in the discontinuous conduction mode is beta into Vs by beta minus d, whereas the average value of the output voltage in the continuous conduction mode is Vs by 1 minus d. So always because the beta is less than 1, so always the average value of the output voltage in the discontinuous conduction mode is always greater than the average value of the output voltage in the continuous conduction mode. And always, whatever the given inductance, if it is lesser than the critical inductance, then also we can say that the current in the inductor is a discontinuous conduction mode. So the critical inductance is equal to R into 1 minus d by 2f for buck converter, R into 1 minus d whole square into d by 2f for boost converter, R into 1 minus d whole square by 2f for buck boost converter. So the critical inductance is equal to R into 1 minus d by 2f for buck converter, R into 1 minus d whole square into d by 2f for boost converter, R into 1 minus d whole square by 2f for buck boost converter. So if whatever the given inductance, if it is lesser than the critical inductance, then we can confirm that simple that is said to be in that discontinuous conduction mode, or either you can check by this also, it indicates that it is in the discontinuous conduction mode. So during on condition, so whenever the switch is on, so the supply voltage is equal to inductor voltage, so VL on is equal to Vs is equal to L into the change in current is delta IL by dt, means T on is nothing but dt. So if you solve this one, we are going to get delta IL is equal to Vs into dt by L. So now I am going to find the average values. So I have already told you the average value of the diode current. The average value of the diode current you can get from the graph, which is half into delta IL into beta minus E into T by T. T cancels, we are going to get delta IL into beta minus D by 2. Similarly, the average value of the inductor current is equal to half into delta IL into beta T by T. So if you solve this one, we are going to get delta IL into beta by 2. Similarly, the average value of the switch current you can get from the graph, which is half into delta IL into dt by T. So you are going to get delta IL into D by 2. And also, the average value of the diode current is equal to the average value of the output current is equal to I0, because the average value of the capacitor current is equal to 0. So the average value of the diode current is equal to the average value of the output current is equal to I0, because the average value of the capacitor current is always equal to 0. Now we are going to apply the power balance equation, which is the input power is equal to output power. So all these things are average values. So Vs into Is average is equal to V0 into I0. So Vs into Is is equal to V0 into I0. So Vs into Is is equal to V0 into I0. So Vs is nothing but, Vs into Is is nothing but, Is is nothing but, which is the IL average. So therefore, Vs into IL average is equal to V0 into I0. You can go for any of this thing. So now we are going to discuss about the buck boost converter. Say buck boost converter in the discontinuous conduction mode we are going to study. So here in the previous buck converter, which is SDL, whereas in the boost converter just you have to interchange by anti-clockwise. So SD and L. But now here just we have to interchange these two items in the buck converter. So inductor is going to come here and diode is going to come here, and just you have to again interchange the diode. So this is the circuit diagram, and this is the load. For load we are going to connect the capacitor, so therefore the amount of change in the output voltage will be very less. So this is the output voltage plus or minus V0, and this is the output current I0, and this is the capacitor current IC, and this is the diode current ID, and this is the inductor current, which is IL, and the voltage across the inductor is VL, and this is the switch current, this is the switch, and this is the switch current, ISW. So whatever the chosen inductance is lesser than the critical inductance, then only discontinuous conduction is possible. Now we are going to basically analyze this circuit. So I have already told you 0 to dt, we are going to turn on the switch. So whenever the switch is turned on, the diode is off. So therefore the inductor is going to get charged. So inductor is going to get charged from 0 to IL max. So therefore, as the switch is on, the source current is equal to switch current, or the switch current is equal to inductor current. So it is also going to follow the inductor current. As the diode is off, so therefore diode current is equal to 0. Whereas from dt to t, yes, we are going to turn off the switch. When the switch is turned off, the diode is on. So therefore the inductor is going to get discharged into the load. So its current is going to get decay. It will be very faster decay before this time t. So therefore we can say before time t only it is going to decay. For small amount of time its current is equal to 0. So we can say this is said to be in the discontinuous conduction mode. So from d to dt, the switch is open. So therefore its current is equal to 0. And the diode current is equal to the inductor current in this stage. So it is also going to follow the inductor current. What is the ripple current? Delta IL and delta IL. So we are going to basically analyze these graphs. So now we are going to analyze during on condition. The switch is on, the diode is off. So whatever the inductor voltage is equal to supply voltage. So VL on is equal to Vs and P on is equal to dt. So during off condition, we can say that the capacitor, or we can say the inductor voltage is equal to, by applying the KVL, we got it is equal to output voltage, and D of is equal to beta minus D into T. So by applying the voltage second balance, or the average value of the output, the average value of the inductor voltage is equal to 0. So VL on P on plus VL of T off is equal to 0. Whereas VL on is equal to Vs and T on is equal to dt plus VL off is equal to, we are going to get V naught, and whereas T off is equal to beta minus D into T is equal to 0. So if we solve this one, we are going to get V naught is equal to minus D Vs by beta minus D. So I have already told you the average value of the output voltage, for the buck boost converter in the continuous conduction mode, which is minus D Vs by 1 minus T. Whereas here, for this buck boost converter in the discontinuous conduction mode, the average value of the output voltage is minus D Vs by beta minus D. So just we have to replace 1 by beta and everything is same. So beta is always lesser than 1. So therefore the average value of the magnitude, we have to take the magnitude value of the average value of the output voltage in the discontinuous conduction mode is always greater than the magnitude of the average value of the output voltage in the continuous conduction mode. So the procedure to check whether a given circuit is in the discontinuous conduction mode or not. So which is the magnitude of the average value of the output voltage in the discontinuous conduction mode is always greater than the average value of the output voltage in the continuous conduction mode, only the magnitude value. So therefore the magnitude value of the average value of the output voltage in the discontinuous conduction mode is always greater than the average value of the output voltage, the magnitude of the average value of the output voltage in the continuous conduction mode. So therefore the V naught average in the continuous conduction mode is minus D Vs by 1 minus D, whereas the V naught average in the discontinuous conduction mode is minus D Vs by beta minus D. And whatever the given inductance is lesser than the critical inductance, then also we can confirm that the given circuit is operating in a discontinuous conduction mode. So these are the two ways by which we can confirm that the circuit is operating in the discontinuous conduction mode. So the critical inductance is equal to R into 1 minus D by 2F for the buck converter, R into 1 minus D whole square into D by 2F for the boost converter, R into 1 minus D whole square by 2F for the buck boost converter. So the critical value of the inductance in the buck converter, which is R into 1 minus D by 2F, for the boost converter, which is R into 1 minus D whole square into D by 2F, whereas for the buck boost converter its value is R into 1 minus D whole square by 2F. So during on condition, whenever the switch is on, VL on is equal to Vs is equal to L into delta L by dt. T on is nothing but dt. So if you solve this one, we are going to get delta L is equal to Vs into dt by L. So we are going to find the average values. So from the graph you can see the average value of the diode current is equal to half into delta L into beta t minus delta t, which is beta minus d into t by t. So if you solve this one, we are going to get delta L into beta minus d by 2. Similarly, the average value of the inductor current is equal to half into delta L into beta t by t. T cancels, we are going to get delta L into beta by 2. Similarly, the average value of the switch current is equal to half into delta IL into dt by t. T cancels, we are going to get delta IL into D by 2. So these are the going to get from the graphs only. So therefore, you can see the average value of the average C simply by applying the KCL, we are going to get ID plus IC plus I naught is equal to 0. So therefore, ID average plus I naught average plus IC average is equal to 0. But IC average is equal to 0. So therefore, the ID average plus I naught average is equal to 0. Because IC average is equal to 0. So therefore, we can simply say that I naught average is equal to I naught. I naught average is equal to I naught is equal to. So I naught average is equal to I naught is equal to minus ID average. ID average, you know, this is the value, just keep the minus. So minus delta IL into beta minus T D by 2. So therefore, ID average plus I naught average is equal to 0. So I naught average is equal to I naught is equal to minus ID average. ID average value just now we have figured out. So minus delta IL into beta minus D by 2. So this is ID, I naught average is equal to I naught is equal to minus delta IL into beta minus D by 2. So now we are going to apply the power balance. The input power is always equal to output power because the devices are ideal. So always you have to go for the average values. So therefore, Vs into Is equal to V naught into I naught. Whereas Is is equal to switch current average value. So therefore, Vs into I switch current average value is equal to V naught into I naught. All these things are the average values we need to consider. So now we are going to study about the multi-phase buck converter. Multi-phase buck converter means here in the continuous conduction mode we are going to study. Multi-phase buck converter means here we are going to cut more than buck converter. More than one buck converter we are going to keep in order to supply the load. Therefore, there are two buck converters. Multi-phase buck converter in the continuous conduction mode. So this is the one buck converter, this is the another buck converter. So SDL. So this is the switch 1, diode D1, inductor L1. Switch 2, diode D2, inductor L2. So here switch current is IS1, inductor current is IL1, diode current is ID1. Here the switch current is IS2, inductor current is IL2, and diode current is ID2. So overall supply current is IS. So this overall supply current is divided into two parts, IS1 and IS2. So here we are going to connect to the load. So you can see clearly this is the load voltage plus or minus V0 and the load capacitor C, and this is the load current is I0. So we are going to basically analyze this circuit. So we are going to basically complementary on the switches. When S1 is on means S2 is off. When the S1 is off means S2 is on. So this is called as the complementary way of switching on the switches. So S1 is on for 0 to T on and it is off for DT to T. So it will be reverse process. S2 is off for 0 to DT and on for DT to T. See, whenever the switch S1 is on and switch S2 is off, what is going to happen? Therefore, the inductor L1 is going to get charged. So inductor L1 is going to get charged, whereas the inductor L2 is going to get discharged. Therefore, IL minimum to IL maximum is going to charge, whereas IL2 maximum to IL2 minimum is going to get discharged. I0 minimum to I0 maximum. Similarly, when the switch S1 is off and switch S2 is on, so inductor L1 is going to get discharged from IL1 maximum to IL1 minimum, whereas the inductor L2 is going to get charged. So therefore, simply we can say that it is going to charge from IL2 minimum to IL2 maximum, whereas the output current is going to get decay. So this is I0 maximum to I0 minimum. So you can see each and everything is continuous. Both the inductor currents are continuous in nature. So this is the continuous conduction mode. So now we are going to analyze these graphs. So we are going to basically analyze the circuits. So during S1 on, so during switch S1 on, what is going to happen? Whenever switch S1 is on, diode D1 is off. So therefore the inductor voltage VL1 on is equal to Vs minus V0, whereas T on is equal to dt. Similarly, when S1 is off, so we can say that the inductor voltage is equal to minus V0. So inductor voltage is equal to minus V0. So VL1 off is equal to minus V0, whereas T off is equal to 1 minus D into T. So therefore, now if you apply the voltage second balance, which is VL1 on plus into T on plus VL1 off into T off is equal to 0, means the average value of the inductor voltage is equal to 0. So if you apply VL1 on is nothing but Vs minus V0, T on is a dt, VL1 on off is minus V0 into T off is 1 minus D into T is equal to 0. So if you solve this one, we are going to get V0 is equal to TVS. So this is same as the single buck. See, if you connect even a just one buck converter, or whether you connect a more than one buck converter in a continuous conduction mode, the average value of the output voltage will remain same. Just V0 is equal to D into Vs. So now I want to find what is the I naught average. So therefore simply you can see that here IL1 plus IL2 is equal to IC plus I naught. IL1 plus IL2 is equal to IC plus I naught. But IC average is equal to 0. So therefore I naught average is equal to IL1 average plus IL2 average. So I naught average is equal to IL1 average plus IL2 average is equal to I naught. I naught is equal to, if you assume load is purely resistive, which is V naught by R. So I naught average is equal to IL1 average plus IL2 average is equal to I naught is equal to V naught by R. So I want to find what is the average value of the switch current. The average value of the switch current. So IS1. So IS1 average is equal to IL1 average into D. These things we have just now discussed. So IS1 average is equal to IL1 average into D. Similarly, IS1 RMS is equal to IL1 average into under root over D. Similarly, ID1 average is equal to IL1 average into 1 minus D. Similarly, ID1 RMS is equal to IL1 average into under root over 1 minus D. Because whenever the switch is on, the inductor current is equal to switch current. Whenever the switch is off, the inductor current is equal to diode current. So based on that thing, we are going to get like this. Similarly, IS is equal to IS of T is equal to IS1 of T plus IS2 of T. So therefore, IS average is equal to IS1 average plus IS2 average. So IS average is equal to IS1 average plus IS2 average is equal to IS. So therefore, IS average is equal to IS1 average plus IS2 average is equal to IS. So now the conclusion, what is the things that we are going to get? See, load sharing increases and the size reduces. So therefore, because by connecting more than one buck converter, the load sharing increases. Means if one buck converter is failed, the other is going to still give the supply to the load. So load sharing increases and also size decreases. So by using this, the overall size is going to get decreased. Suppose load shared equally. Suppose now we will discuss a special case. What is the meaning of this one? Load shared equally and both the inductance are equal because ideal. Then what is going to happen? Load shared equally and both the inductance are equal means both are having the same inductive current. So therefore, IL average is equal to IL2 average is equal to I naught by 2 because both are equal. Because both are pure, both are having the same inductance and also they are going to share the load equally. So therefore, IL1 average is equal to IL2 average is equal to I naught by 2. Similarly, IS1 average is equal to IS2 average is equal to IS by 2. That is the meaning of this one. Whenever the load is shared equally and the two circuits are identical, it indicates that IL1 average is equal to IL2 average is equal to I naught by 2. Similarly, IS1 average is equal to IS2 average is equal to IS by 2. So now I am going to apply the power balance for the input and also output because all the devices are ideal. So Pn is equal to P naught. Always you have to take the average values. So Vs into Is is equal to V naught into I naught. Here all the things are average values. So Vs into Is average is equal to V naught into I naught. So here V naught is equal to D into Vs. Whereas similarly I naught is equal to V naught by R. Again V naught is equal to dVs. So we are going to get D into Vs whole square by R. So Vs cancels. We are going to get Is average is equal to D square into Vs by R. So this is the average value of the source current, which is Is average is equal to D square into Vs by R. So this is the thing that you need to easily remember. So now we are going to discuss about the class A chopper. I have already told you regarding the class A chopper here. In the class A chopper, the graph between V0 and I0 is going to lie purely on the first coordinate. Then it is said to be a class A chopper. But in the class B chopper, the graph between the V0 and I0 is going to lie in the second coordinate. So before that we will discuss the circuit here. So this is the circuit of the class B chopper. So this is plus or minus Vs. This is a plus or minus V0. So this is the load which is L and E. This is the diode and this is the chopper. See, always the supply voltage is always constant for all the time. The supply voltage is a DC value, so it is a constant for all the time. And here I am going to trigger the chopper for some amount of time and then I am going to off for some amount of time. See, when the chopper is on, when the switch is on, you can say that V0 is equal to 0. When the chopper is open, you can say that as the chopper is open, you can say that simply here whatever the supply voltage is equal to V0. So whatever the supply voltage is equal to V0. So therefore, whenever the chopper is on, the output voltage is equal to 0. Whenever the chopper is off, the output voltage is equal to supply voltage. So whenever the chopper is on, the inductor is going to get discharged. Or we can say that the inductor is going to get charged in the negative direction. So therefore, the inductor is going to charge in the negative direction. So therefore, current is going to get increased. The current is going to get increased in the negative direction. So current is going to get increased. Whenever the chopper is open, the inductor is going to get discharged. The inductor is going to get discharged. So we are going to get a waveform in this fashion. So whenever the chopper is on, the output voltage is equal to 0 and the inductor is going to get charged in the reverse direction. So therefore that is the meaning of this one. But whenever the chopper is open, the output voltage is equal to supply voltage and the inductor is going to get discharged. So this is the graphs we are going to get. The output voltage and also the output current. So now we are going to discuss in another few basics manner. So what happens when the chopper is on? So when the chopper is on, so you can see clearly when the chopper is on, indicates that the diode is off. So because it is reverse bias, so diode is off whenever the chopper is on. So therefore you can see clearly the output voltage is equal to 0 and the current will be negative because the current will try to flow in this manner. But I know we have taken the reverse manner, so therefore current I will be negative. So therefore inductor will be charging. Whereas when the chopper is off, means diode is going to get conduct. So the output voltage is equal to supply voltage and the current will be negative and it is going to get discharged because now inductor is going to get discharged. The current in the inductor is going to decrease. It is going to decrease means actually the current is going to flow in this manner. But you have taken current in this direction, so it will be negative current. So it will be discharging. So now you can see clearly that the average output voltage is always positive. So you can see clearly the output is always positive. The output voltage is always positive, whereas the output current is always negative. So because of that only we are going to get the plot between the V0 and I0 in the second coordinate. Because current is negative and the V0 is always positive, so we are going to get the second coordinate. So that is the result is called as a class B chopper. So because of this reason only V0 is always positive, whereas the current is a negative. So because of this only we are going to get a second coordinate operation. So this is called as a class B chopper. So we have discussed about the class A chopper and the class B chopper. So class A chopper means it is lying in the first coordinate. Class B chopper means it is lying in the second coordinate. Whereas the class C chopper means it is going to lie in the first coordinate and also second coordinate. The combination of first coordinate and second coordinate is called as the class C chopper. So now we are going to discuss the class C chopper. So this is the circuit diagram of the class C chopper. So there is a supply voltage, constant supply voltage Vs, and there is a load of RLA load. So here chopper 1, chopper 2, diode D1 and diode D2. So from this we are going to connect to a load. So now we are going to discuss the circuit of this one. How the things are going to happen, we are going to see. See, the supply voltage is always constant for all the time. So here I am going to see, this is the thing that you need to be very careful. I am going to on the chopper 1 and chopper 2 is off. Then what is going to happen when the chopper 1 is on? So you can see clearly from the circuit diagram, that is chopper 1 is on and the chopper 2 is off. So what is going to happen? The output voltage is equal to. So you can see clearly the chopper 1 is on and the chopper 2 is off. And also D1, D2 are also off. So only chopper 1 is on and chopper 1 is on and remaining everything is off. So remaining everything is off. Only chopper 1 is on. So therefore, as a chopper 1 is on and chopper 2 and diode D2 and diode D1 are all are off except chopper 1. Then we can say that the current is positive and the voltage is also positive. So V0 is equal to Vs. So V0 is equal to Vs and the current in the load is going to get increased. The inductor is going to become in a charging mode. So therefore current is going to get increased. In the second period, you can see that the chopper is off. So chopper 1 is off, chopper 2 is also off, and also diode D2 is also off. Only diode D1 is on. So only diode D1 is on. So only diode D1 is on. So therefore we can say that output voltage is equal to 0 and the current in the inductor is going to get decay. So therefore it is going to decay means the inductor is in the discharging mode. So it is going to get decay. Similarly here again chopper 2 we are going to on. The chopper 1 is off, D2 is off and D1 is off. Only chopper 2 is on. So if chopper 2 is on, what is going to happen? So only if chopper 2 is on, you can see clearly from the circuit that only chopper 2 is on, remaining everything is off. So therefore the output voltage is equal to 0. output voltage is equal to 0. So therefore the current in the inductor will be in the negative direction. It is going to charge in the negative direction. So therefore inductor will be in the charging in the reverse direction. Similarly here what we are going to do basically here now in the last case diode D2 is on. So diode in the last case chopper 1 is off, chopper 2 is off, and D1 is off, and only D2 is on. So only the D2 is on. So therefore the output voltage is equal to Vs. Output voltage is equal to Vs, and also the output current is negative, and it is going to get decay because it is going to become decay because of the supply voltage. It is going to decay in the reverse direction. So you can see clearly the current is positive and the current is negative, whereas the output voltage is always positive. So output current is positive and also negative, whereas the output voltage is always positive. So because of this reason only it is going to cover both the first quadrant and also the second quadrant. So therefore this is called as a class C chopper. So listen carefully. In the first case, the only chopper 1 is on and everything is off. Chopper 2 is off, D1 is off, and D2 is off. So therefore from the circuit diagram we can say that the output voltage is equal to Vs. The output voltage is equal to plus Vs. So therefore the output current is going to get charged. So inductor is going to get charged. So therefore I0 is positive. In the second case, we can say that so chopper CH1 is off, chopper 2 is off, and D2 is off. Only D1 is on. So only D1 is on. So therefore we can say that inductor is going to discharge in mode. So current is going to get decay. Only D1 is on. So output voltage is equal to 0. The current is going to get decay. So therefore current is going to get decay. In the third case, chopper 2 is on. So remaining everything is off. So only chopper 2 is on. Remaining everything is off. So because of the RLE load, because of the presence of RLE load, this voltage is present inside the load. So because of that, the current will be in the reverse direction. So it will be inductor is going to charge in the reverse direction. So therefore current will be negative. But it is in the charging. So I0 is equal to negative. So therefore we can say that finally everything is off except D2. So D2 is the only thing which is on. So therefore when D2 is on, V0 is equal to plus Vs and I0 is equal to negative, and it is going to get discharged. Inductor is going to get discharged. So therefore we can see clearly the current is a positive and also negative, whereas the output voltage is always positive. So therefore it is going to cover the first quadrant and also the second quadrant. So we can say this is said to be class C chopper. So output voltage is a positive, it is always positive, whereas the output current can be positive, can be negative. So because of this reason only we can say it is said to be class C chopper. So now we are going to discuss the class D chopper. See, class D chopper means basically we have learned about the class A. Class A means first quadrant, class B means second quadrant, class A means both the first quadrant and also the second quadrant. So now we are going to discuss the class D chopper. It means first and fourth quadrant. So you can see clearly this is a circuit diagram. So this is a supply voltage plus or minus Vs. So this is chopper 1, chopper 2, diode D1 and diode D2. So this is the load. The load voltage is plus or minus V0 and the load current is I0. Let me assume the load is RLE load. So now we are going to analyze the circuit and we are going to see each and every aspect of this one. So we can see clearly the supply voltage is constant for all the time. The supply voltage is constant for all the time. So now here we are going to on the two choppers. Chopper 1 and the chopper 2 are both on at the same instant. So chopper 1 and chopper 2 are on. So you can see clearly from the circuit diagram. So therefore the output voltage is equal to Vs. So output current is a charging mode. So it means the inductor is in the charging mode. So therefore I0 is positive. So therefore we can see clearly the output voltage is equal to Vs and the current is going to in the charging mode. So therefore current in the inductor is in the charging mode. So therefore it is increasing. So in the first case, chopper 1 and chopper 2 both are on and D1, D2 are off. So therefore V0 is equal to Vs and I0 is equal to positive, means inductor is charging. In the second case, you can see clearly both the choppers are off. So therefore if both the choppers are off, means diode D1 and diode D2 are going to conduct. So diode D1 and diode D2 are going to conduct. Chopper 1 and chopper 2 are off. So therefore we can say that the output voltage is again, therefore the output voltage is equal to now minus Vs. So output voltage is equal to now minus Vs and the current is again positive. So current is again positive, but now the current is going to get decay because inductor is going to get discharged. So therefore current is going to get decay. So therefore L will be in the discharging. So in the first case, both the chopper 1 and chopper 2 are on. So therefore V0 is equal to plus Vs, and the current will be in the positive, but it is the inductor is going to become charged. So current is going to get increased. In the second case, the chopper 1 and the chopper 2 are off. Only diode D1 and diode D2 are on. So therefore V0 is equal to minus Vs, and also the current is going to get decay. The current is going to get decay. So therefore we can say clearly that current is going to get decay, means discharging. So in the case of the discharging. So it is going to repeat for all the time. So we can say that the output voltage is positive and also negative, but the output current is always positive. So therefore this is called as the first and fourth coil. So therefore the first coil and also fourth coil are covered. So this is called as the class D chopper. So class D chopper is going to cover both the first coil and also the fourth coil. So we have discussed class D chopper means first coil, class B means second coil, class C means both the first and second coil, and class D means first and fourth coil. So now class C means each and every coil, means all the four coils. So class A means first coil, class B means second coil, class C means both the first and second, class D means first and fourth, and class C means all the coils. So this is the class C chopper. It is going to cover all the coils. So we are going to see the circuit in a very detailed manner. So therefore there are chopper 1, chopper 2, chopper 3 and chopper 4. There are diode D1, diode D2, diode D3 and diode D4. So this is the load, which is RLE load, plus or minus V0, and this is the I0 current. So now we are going to analyze this circuit. So this is the output voltage and this is the output current. So we are going to see each and everything. So in the first case, chopper 1 and chopper 2 are on. So whenever the chopper 1 and chopper 2 are on and remaining everything is off. So chopper 2, chopper 3, D1, D2, D3, D4, everything is off. Only chopper 1 and chopper 2 are on. So we can see clearly from the circuit. So therefore V0 is equal to plus Vs, and the inductor will be charging mode. So I0 is going to get increased. So V0 is equal to plus Vs, and the inductor is in the charging mode. So current is going to get increased. In the second case, D3, D4 are on. So D3, D4 are on. It indicates that D3, D4 are on means remaining everything is off. So D3, D4 are on means remaining everything is off. So chopper 1, chopper 2, chopper 3, chopper 4 are off, and also D1, D2 are also off except D3, D4. So only D3, D4 are on. So we can see clearly from the circuit diagram. So therefore V0 is equal to minus Vs, and the current in the inductor is going to get discharged. It is going to decay. So therefore current is going to get decay, and V0 is equal to minus Vs. In the third case, chopper 3 and chopper 4 we are going to on. So chopper 3 and chopper 4 we are going to on. So whenever the chopper 3 and chopper 4 are on and remaining everything is off, which is chopper 1, chopper 2 off, chopper 1 off, chopper 2 off, and also D1, D2, D3, D4, everything is off. Then we can see clearly that output voltage is equal to minus Vs, and the current in the load is going to get increased in the reverse direction. So current in the load is going to increase in the reverse direction. So therefore current is going to get increased in the reverse direction. Means inductor is in the charging mode but in the reverse direction. So current is going to increase in the reverse direction. So now in the last case, D1, D2 are on. So D1, D2 are on. So whenever the D1, D2 are on, means remaining everything is off. Remaining all the choppers and the remaining all the diodes are off except D1, D2. So therefore we can say that V0 is equal to plus Vs. So V0 is equal to plus Vs, and the current will be in the negative. It is discharging in the negative direction. It is discharging in the negative direction. So therefore V0 is equal to plus Vs, and the current is going to discharge in the negative direction. So we can say clearly in the first case, chopper 1 and chopper 2 is on and remaining everything is off. So therefore V0 is equal to plus Vs, and the current in the inductor is in the charging mode. It is going to get increased. So V0 is equal to Vs, and the current is going to increase in the positive direction. Whereas in the second case, D3, D4 are on. So D3, D4 are on means remaining everything is off. So therefore we can say that V0 is equal to minus Vs, and also now the current in the inductor is going to get discharged. It is going to discharge in the positive direction. So it is going to discharge, and V0 is equal to minus Vs. In the third case, chopper 3 and chopper 4 are on. So therefore V0 is equal to minus Vs, and also now the current in the inductor is in the charging mode but in the reverse direction. So in the reverse direction, V0 is equal to minus Vs. Whereas in the fourth case, D1, D2 are on. So whenever D1, D2 is on, V0 is equal to plus Vs, and the current in the inductor is going discharge in the reverse direction. So therefore, discharge in the reverse direction. So therefore, this is the thing we are going to get. So you can say clearly the output voltage is a positive, it is also negative, and the output current is also positive and also it is negative. So therefore, plus means first coordinate. So plus means first coordinate. Here plus and this is minus. So therefore, this is plus and this is minus means fourth coordinate. So therefore, here this is minus and minus means third coordinate. This is minus and this plus means second coordinate. Yes, it is going to cover each and every coordinate. So x-axis is current, y-axis is voltage. So plus means first coordinate. So plus minus means fourth coordinate. Minus means third coordinate. Minus plus means second coordinate. So it is going to cover each and every coordinate. So it is called as the class A chopper. So it is going to cover each and every coordinate. So it is called as a class A chopper. So now we are going to discuss one more important concept, which is the class A chopper with RLE load in the continuous conduction mode. So class A chopper with the RLE load in the continuous conduction mode. Continuous conduction means here we are going to choose the inductance of very large value. Continuous conduction means we are going to choose the inductor of very large value. So this is the output voltage, which is plus or minus V0. So this is the class A chopper. Class A chopper means like step down chopper, S, D, N. So like that. So this is the class A chopper means always V0 is positive and I0 is always positive. That is the meaning of the class A chopper. So here plus or minus Vs, this is the chopper and this is the freewheeling diode and this is the output current with the RLA low. L value is very high, so therefore continuous conduction is possible, and this is the output voltage plus or minus V0. So now we are going to analyze this circuit each and every thing. So you can say clearly the supply voltage is constant for all the time. It is constant for all the time, and this is the this chopper we are going to on. So for 0 to T on we are going to on this chopper, and from T on to T we are going to off this chopper. Means the switch is on only for 0 to T on, and from T on to T we are going to off this chopper or the switch. Whenever the chopper is on, so therefore the output voltage is equal to supply voltage. In that time freewheeling diode is off, so therefore the output voltage is equal to Vs, and the current in the inductor is in the charging mode, so current is going to increase from minimum value to maximum value. So I0 is going to increase from I minimum to I max. Whenever the chopper is off, the freewheeling diode is going to get connected and the current in the inductor is going to get decay. It is in the discharging mode, so it is going to get discharged. So current is going to get decrease from T on to T. So same thing is going to repeat again and again. So here as the L is large, so the current is not at all equal to 0 for not even one time. So we can say continuous conduction means 0 is not at all present in the output current. That is the meaning of this one. So the amount of ripple, maximum value minus minimum value is the amount of ripple is delta A. Delta A means it is the amount of ripple in the output current. So we are going to analyze the circuit. As I already told you, whenever the chopper is on, so whenever the chopper is on means freewheeling diode is off. So therefore the output voltage is equal to Vs, and the inductor is in the charging mode. So current is going to increase from I minimum to I maximum. So therefore I0 is positive. When the chopper is off, means the freewheeling diode is on. So therefore V0 is equal to 0. L is in the discharging mode. So current is going to get decrease. So you can say clearly the output voltage is always positive and the output current is also positive. So we are going to get only the first coordinate. That is the reason it is called as a class A chopper. So I want to find what is the average value of the output voltage. So average value of the output voltage is equal to Vs into T on by T. So T on by T is called a duty ratio. So D into Vs. So V0 average is equal to D into Vs. So now I want to write the time domain expression of the output voltage. So V0 of T is equal to, so V0 of T is equal to R into I0 of T plus VL plus E. This is the time domain expression of the output voltage. V0 of T is equal to I0 of T into R plus VL of T plus E. So if I want to find the average equation, if I want to write the average equation of this time domain, so V0 average is equal to R into I0 average plus VL average is nothing but 0, because the average value of the inductor voltage is always equal to 0. As E is a DC value, it is always constant, so its average is again E. So therefore V0 average is equal to I0 average into R plus E. So therefore I0 average is equal to V0 average minus E by R. But we have already know V naught average is equal to D into Vs. So D into Vs minus E by R. So this is called as the I naught average. So I naught average is equal to V naught average minus E by R, and V naught average is equal to D into Vs. So D into Vs minus E by R. So we are going to analyze the circuit when the chopper is on. So when the chopper is on means the chopper is on for a period of T lies between 0 to T on. Only this time the chopper is on. So therefore the output voltage is equal to Vs. So I want to write the time domain expression of the output voltage. So output voltage is equal to R into I naught of T plus L into D I naught of by dt plus E is equal to V naught of T. Means I am going to write the time domain expression of the output voltage. So V naught of T is equal to I naught of T into R plus L into E I naught of T by dt plus E. Because in this time the output voltage is equal to Vs. So we are going to get this expression. The time constant of the circuit is nothing but tau is equal to L by R. So this is a first order differential equation. So you are going to get basically the complementary solution and also the particular integral solution. So if you solve this one, we are going to get I naught of T is equal to some complementary solution, which is K into e to the power of minus T by tau, and the particular solution is Vs minus E by R into 1 minus e to the power of minus T by tau. So this is the particular solution and this is the complementary solution. So this is the expression we are going to get I naught of T. But at T is equal to 0, I naught of 0 is equal to I minimum. So if you substitute here at T is equal to 0, I naught of 0 is nothing but I minimum. So if you substitute T is equal to 0 and if you substitute T is equal to 0 and I naught of 0 is equal to I minimum, then we are going to get K is equal to I minimum. So K is equal to I minimum we are going to get. But at T is equal to T on, if you substitute T is equal to T on, then I naught of T on is nothing but which is I maximum. So in place of T, substitute T on. At that condition, I naught of T on is nothing but which is I maximum. So if you solve this one, we are going to get finally an equation in this format, which is I max is equal to I minimum into e to the power of minus T on by tau plus Vs minus E by R into 1 minus e to the power of minus T on by tau. So this is the expression that we are going to get finally. So now we are going to analyze the circuit when the chopper is off. So when the chopper is off means chopper is off for a period of T lies between T on to T. So now I am going to convert into another time. I want to convert in terms of another time, which is T dash, which is going to lie between 0 to T off. Means I am going to convert this into another time domain, which is T dash 0 to T off. So in that time, the diode is conducting, so therefore the output voltage is equal to 0. So now I want to write the time domain expression. V naught of T is equal to I naught of T into R plus L into D I naught of T by dt plus E, but V naught is equal to 0. So here also you are here also we are going to get the complementary solution and also the particular solution. So complementary solution is in terms of T dash we are going to write I naught is equal to K into e to the power of minus T dash by tau plus minus E by R and minus e to the power of minus T dash by tau. But at T dash is equal to 0. At T dash is equal to 0 means we can say that I naught of T dash is equal to I max. Because see at T dash is equal to 0. So at T dash is equal to 0 means here we are going to get the condition of I max. So therefore I naught of 0 is equal to which is I max. So if you substitute in this expression T dash is equal to 0, so we are going to get basically I naught is equal to I max. So if you substitute we are going to get K is equal to I max. Whereas at T dash is equal to T off, if you substitute at T dash is equal to T off, so I naught of T off is nothing but it is equal to I minimum. So if you substitute here, we are going to get the equation in this format. I minimum is equal to I maximum into e to the power of minus T off by tau minus E by R into 1 minus e to the power of minus T off by tau. So this is the expression that you are going to get, because T dash is equal to 0 means I am going to get I naught at that point which is equal to I maximum. So if you get K is equal to I maximum, if you substitute T dash is equal to T off, then we are going to get finally that it is at I dash I naught at T off is nothing but we are going to get I minimum. So if you substitute we are going to get this equation. The chopper is on, we got the equation which is I maximum is equal to. So basically we got the two equations, the above one and the second one. So these two equations with two unknowns. So two equations with two unknowns, I max and I minimum. So if you solve these two equations, finally we are going to get I max is equal to Vs by R into 1 minus e to the power of minus T on by tau by 1 minus e to the power of minus T by tau minus E by R. And similarly, I minimum is equal to Vs by R into e to the power of T1 by tau minus 1 by e to the power of T by tau minus 1 minus E by R. So by solving this above two equations, when the chopper is on, we got one equation, the chopper is off, we got another equation. So two equations with two unknowns, I minimum and I maximum. So by solving these two equations, we are going to get these two equations, I max and I minimum. Whereas T is nothing but T on plus T off. I want to find what is the amount of ripple present in the output current. So delta I is equal to I max minus I minimum. So you know maximum value and you know minimum value. Just do the subtraction of these two things, we are going to get finally delta I is equal to Vs by R into 1 minus e to the power of minus T1 by tau into 1 minus e to the power of minus T off by tau by 1 minus e to the power of minus T by tau. Now I am going to assume I base is equal to Vs by R and delta I per unit is equal to delta I by I base. I am going to assume like this. This Vs by R is nothing but I base and delta I by I base is nothing but delta I per unit. I am going to assume. So finally I am going to get delta I per unit is equal to, so this you are going to get, which is 1 minus e to the power of T1 is nothing but dt. So minus dt by tau into 1 minus e to the power of T off is nothing but minus of 1 minus d into T by tau by 1 minus e to the power of minus T by tau. So this is the thing that you are going to get. So this equation is a function of d. So delta I per unit is a function of d. So as you increase the d, slowly from 0 to 0.5, the delta I per unit is also going to get increased. But at d is equal to 0.5, you are going to get the maximum value in the ripple current. But if you increase further above 0.5, the delta I per unit is going to get decreased. It indicates that simply the delta I is going to increase from 0 to 0.5 and after that it is going to get decreased. So at 0.5 it is going to have the maximum ripple in the output current. So maximum ripple in the output current is possible when d is equal to 0.5. So now condition for boundary operation. So what is the condition for boundary operation means? I want the minimum value to be 0. The current minimum value to be 0. When? See, one is the minimum value of the current is equal to 0 because if you got expression I minimum. So in that I minimum, if you substitute I minimum is equal to 0 and if you do the simplification, finally you are going to get this equation which is T1 is equal to tau into log of 1 plus m into e to the power of T by tau minus 1 with a base E. So now here there is a particular d dash where m is called as the E by Vs. So m is the ratio of E by Vs. So there is a particular d dash. This particular d dash is a T1 by T. So divide by T on both sides. So tau by tau into log of E 1 plus m into e to the power of T by tau minus 1. So for this duty ratio, the I minimum will be equal to 0. So this is the duty ratio at which the minimum current will be equal to 0, which is tau by T into log of 1 plus m into e to the power of T by tau minus 1 with a base E, where m is the E by Vs. So in the I minimum expression, I kept the I minimum is equal to 0. So after simplification, I got this value, m is equal to E by Vs. But I want the particular d dash. What is the particular d for which the I minimum is equal to 0? So that particular d is called as the d dash, which is T1 by T. At this particular d dash only, I am going to get the I minimum as 0. So this is the particular duty ratio, which is d dash. So if d is greater than d dash, then it is continuous operation. If d is less than d dash means, then it is discontinuous operation. So always you have to operate the duty ratio which is greater than this critical value. Then only we are going to get the continuous operation. Otherwise, if the duty ratio is lesser than the critical value or the boundary operation, then discontinuous operation is going to present in the output current. So now we are going to discuss the class A chopper with RLE load in the discontinuous conduction. In the previous case, we have known the class A chopper with RLE load for continuous conduction, but here we are going to discuss the same circuit, but only thing is here discontinuous conduction means the value of the inductor in the load is very small. So because of that reason only, a discontinuous conduction is present in the output current. That is the meaning of this one. So same circuit is your chopper, freewheel diode, voltage source, relay load, RL and E. This is the output voltage plus or minus V0. So now you can say clearly that the supply voltage is always constant for all the time. So now here I am going to trigger the chopper for small amount of time. Then when the chopper is on, means freewheeling diode is off. So therefore the output voltage is equal to supply voltage. The output voltage is equal to supply voltage for 0 to T on. So inductor is in the charging mode. So inductor current is going to increase from 0 to I max. So when T on to T off means I am going to turn off the chopper. This chopper is open. So therefore the inductor is going to discharge through this freewheeling diode. The inductor is going to get discharged through this freewheeling diode. So because of that, the current is going to decrease. So the current is going to get decrease. As the L is very small, it is going to decay very faster in T on to Tx. In T on to Tx only, it is going to decrease. So in this duration, T on to Tx, freewheeling diode is conducting. So therefore the output voltage is equal to 0. After that, what is going to happen is, after that current is going to become 0. After that Tx to T, the current is equal to 0. It is going to become 0. As the current is equal to 0, so simply we can say that the output voltage is equal to E value. So output voltage is equal to E. So this is the thing we are going to get. So this is the output voltage and this is the output current we are going to get. So now we are going to do the analysis of this circuit. So for 0 to T on, I already told you the chopper is on and the freewheeling diode is off. So therefore the output voltage is equal to source voltage and the inductor is in the charging mode. So output current will be positive. It is increasing from 0 to I max. From T on to Tx, the freewheeling diode is conducting and the chopper is off. The inductor is discharging. So as the L value is very less, it is going to decay very faster. So therefore V0 is equal to 0 and I0 is positive but L is discharged. Whereas from Tx to T, as the chopper is off, now the current in the inductor is also 0. So therefore diode is also off. So therefore simply we can say that the output voltage is equal to E and the output current is equal to 0. So now if I want to find what is the average value of the output voltage, so from the graph we can say that which is Vs into T on plus 0 into Tx minus T on plus E into T minus Tx by total time period T. So we are going to get D into Vs plus E into 1 minus Tx by T. Whereas T1 by T is called as the duty ratio. So therefore Vs into D plus E into 1 minus Tx by T. This is called as the average value of the output voltage whenever the discontinuous conduction is present. So whereas if you want to find what is the RMS value of the output voltage, so RMS value of the output voltage is equal to under root over 1 by T into which is Vs square into T on plus E square into T minus Tx. This is the value. So V0 RMS is equal to under root over 1 by T into Vs square into T on plus E square into T minus Tx. So if you do the simplification, we are going to get which is under root over D into Vs square plus E square into 1 minus Tx by T. So this is the RMS value of the output voltage. Now we are going to discuss in a step-up operation the condition for controlled power transformer. In a step-up operation, the condition for controlled power transformer. So this is called as a step-up chopper, SDL. So this is a step-up chopper. So this is the DC source Vs and this is the motor. Suppose motor is acting in a regenerative braking. Suppose if this DC motor is acting in a regenerative braking, means the speed is more than the no-loop speed. So because of that, what is going to happen? The generated voltage is very high. It is very higher than the supply voltage Vs. So because of that, the current will be opposite. So therefore current is going to flow from this motor to this source. So therefore this is going to accept the energy from this motor. This is used only in the case of the regenerative braking. So whenever the motor is operating in the regenerative braking, means the speed is very higher. So induced EMF is very higher. So therefore current will be flowing in the reverse manner. So therefore this machine is going to act like a DC generator and it is going to deliver the power from motoring to the Vs. So current can flow only from E to Vs only when E is greater than Vs. So therefore Vs is always less than E, or simply we can say that 0 less than Vs less than E. The principle of step-up chopper can be employed for the regenerative braking of DC motors. The principle of step-off chopper can be employed for the regenerative braking of DC motors. So whenever the regenerative braking is occurred, we can utilize that power for giving the power to the supply voltage. So therefore we are going to give the supply whenever the motor is operating in the regenerative braking. We are going to supply that power to this source. So when chopper is on, inductor stores the energy, and then when chopper is off, inductor releases the energy to the source. The voltage E by 1 minus D exceeds Vs. So DC machine begins to work as a DC generator and armature current I flows opposite to motoring mode. See, whenever the average output voltage is equal to input voltage by 1 minus D, input voltage is here E, so E by 1 minus D. If this is greater than the Vs output voltage, we can say that this motor is going to act like a DC generator and it is going to operate in a regenerative braking. So therefore it is going to deliver the power from the motor to the source. Now flows from DC machine to source Vs causing regenerative braking of DC motor. So for step of operation means current should flow from E to Vs only when E is greater than Vs, or simply Vs is lies between 0 to E. So now we are going to discuss about the single phase AC voltage controller feeding a resistive load. So this is a single phase supply AC voltage controller feeding a resistive load. So this is a resistive load, and here this is called as a AC voltage controller. This is a triac we are going to use. So single phase AC voltage controller feeding a resistive load. So this is a triac we are going to use. So this is the source current IS and this is the load current I0. So this is the gate. This is a triac. So therefore this is the output current I0 and this is the output voltage V0. So this is the input voltage Vs. Vs is equal to Vm sin omega t. So you are going to get in this fashion. So triac is going to have two thyristors in the opposite manner. So here T1 is triggered at alpha and T2 is triggered at pi plus alpha. So therefore whenever the T1 is triggered, so V0 is equal to Vs. So V0 is equal to Vs. Whenever the trigger, when we trigger the T2, again V0 is equal to Vs. So again V0 is equal to Vs. In these regions, both are thyristors are absent or they are going to get turned off. So because of that, it opens circuit. So therefore output voltage is equal to 0 in this manner. So if you want to find what is the RMS value of the output voltage, so RMS value of the output voltage is equal to integration of 1 by 2 pi, 2 times of integration of alpha to pi Vm sin theta whole square into d theta. So if you solve this one, we are going to get Vm by under root over 2 pi under root over pi minus alpha plus sin 2 alpha by 2. So always the input power is equal to output power. So input power is equal to Vs Is cos phi. So RMS value of the input voltage into RMS value of the input current into cos phi is equal to output power is equal to V0 RMS into I0 RMS, because it is a resistive load. So therefore power factor is equal to 1. So therefore Is is same because Is is equal to I0 for all the time. So their RMS is also equal. So these are going to get cancelled. So therefore cos phi is equal to V0 RMS by Vs RMS. So input power factor is equal to cos phi is equal to output RMS by input RMS. So output RMS, just now we have seen input RMS is Vm by root 2. So if you do the ratio, we are going to get 1 by root pi under root over pi minus alpha plus sin 2 alpha by 2. So therefore this is the RMS value of the output voltage and the RMS value of the input voltage is Vm by root 2. So if you do the division of these two things, we are going to get 1 by root pi under root over pi minus alpha plus sin 2 alpha by 2. So this is the input power factor. So if you want to find how much amount of power absorbed by the load, the amount of power absorbed by the load is equal to V0 RMS whole square by R. So V0 RMS value we know, just do the square and do the division by R. So we are going to get this much amount of power is absorbed by the load. So by this lecture we have successfully completed some of the important formulas of the choppers in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, the direct notice comes to your mobile. If any improvements needed in the video lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Please take care. Bye bye.